So Nlp, you need to swap the presenter view.
Oh, I see. So right now you see my presenter view, right?
Yeah.
Okay. So should be on the bottom, in the up of the.
Yeah, now it's correct. Okay, perfect.
Okay, it's already 11 o'clock, so let's start our tutorial. Hello, everyone. Good morning, good afternoon, good evening, depends on where you are. Today I'm very, my name's Linfield. Today I'm very delighted to welcome you to our DLG4NLP tutorial. We'll talk about deep learning on graph for natural language processing. This is joint with Yuchen from the Facebook, NG from the UIUC and Amazon, and Yunya Li from the IBM Research. Okay, this is the outline for our tutorial today. So we will first talk about the motivation why we try to do DLG for NLP. So why graph is an NLP, and what's a conventional machine learning method for NLP, and what's a modern approach, for example, deep learning on graph and foundation and models. And after we introduce the basic motivation and method, background knowledge, we will talk about the core foundations for our DLG for NLP. We will talk about how to convert the text sequence to graph structure data. So we call it graph construction for NLP. And once we have graph, so the next step will be how can we choose a proper graph representation learning technique for NLP. And furthermore, we will introduce encoder-decoder model. That is one of the most important branch for NLP. And we'll talk about what's a graph-based method for the encoder-decoder models. After we introduce our foundations, we will talk about various applications that have been leveraged the power of the, for example, graph neural nets for the NLP domain. We have been selected 5 representative applications: the information extraction, for example, semantic parsing, machine learning comprehension, natural language generation, and machine translation. So after that, we will also have a demo demonstration part. So where we will introduce our new graph for NLP library that is a design for easy use of the graph neural nets for NLP. And you will learn how to use this library through our demo. And then finally, we will present the future direction for this exciting area and to conclude this tutorial. Okay, so let's first start our introduction. So first of all, people often ask, so why shall we study graph? That's because the graph is a generic language for describing and modeling complex system. As shown in the right-hand side, the graph is a very simple data structure. So each of the graph node represents some object, and the edge here is trying to describing the relationship between different nodes. So let's take a concrete example. Imagine this is a teacher-student node graph. Okay, in this node graph, some node is represented as a teacher, and some node is represented as a student. And for each of the graph node, they also have their own attribute. For example, if this teacher node, so the attribute could be, what kind of classes the teacher is teaching, and what's the ranking level for this teacher, and what's the gender information for a teacher. Similarly, for students, they also have their own attribute. When we talk about deep learning on graph, we essentially talk about a group of the method that will take the graph topology and also the graph node attribute information as an input, and then to learning the representation for each of the graph node to do the downstream tasks. So graph structure data today is everywhere, ranging from the internet to social network. Naturally, everything is connected as a graph. In the financial domain, we can see clearly that we can formulate a financial transaction graph that between each financial institution and their customers. In the biomedical domain, people have been trying to leverage the graph machine learning to model the chemical compound as a graph, and then try to generate a new graph that essentially can be represented as a new drug for the drug discovery. People also have been leveraging, for example, use the data flow graph or the control flow graph to do the program analysis, even in the computer vision domain. So when we, as shown in this figure, although the convolutional neural network have been achieved great success, if we try to do the reasoning over this image, people have found that graph neurons have been very helpful to do this high-level reasoning activities. Graph also is ubiquitous in NLP domain. As you can see that, so there are many different graphs that have been studied in the NLP domain. So for example, the dependency graph and continuity graph that essentially can be used to describing the syntactic information, structure information inside a text sequence. You can also using like AMN graph and IE graph, try to represent the semantic relationship inside a text sequence. Even in a very specific domain like a logic form, here we can represent SQL as SQL graph, so that we can leverage the particular structure information using graph-based machine learning technique. So now let's talk about the conventional machine learning technique on graph for NLP. So this is not new at all. So the machine learning on graph for NLP have been extensively studied over the last 2 decades. So at the very beginning, people tend to represent the natural language as back of the token. So as it's shown in the right-hand side, right, we have 3 different sentences. So welcome to attend our DLG4NLP tutorial and all these other sentences. And so the typical way to do that is to derive them into back of the token. And then, for example, you can use a backward word or TF-IDF to create a sparse vector representation to present each sentence. And later people found that, so we can also represent natural language as a sequence of tokens that essentially try to represent each of the word token as using a dense vector. And people found that, so this has been very useful to capture the semantic meaning of each word token. That is essentially it's ranging from word vector, a global vector, this word embedding technique. And since that, people have been found that so this is extremely useful for all the NLP applications. We can also represent natural language as a graph. So as we mentioned before, so all these different graphs that can capture either syntactic information or semantic information. And we can easily also build a text graph that may have a multiple hierarchy. As shown in the right-hand side, as imagine that you have a document may have a multiple sentence. So each sentence you can treat it as a graph node, as a sentence node. And then for each of the sentence, you may have a multiple word token, and then each word token will link to this sentence. So you can create this hierarchical text graph. So there are many methods that is based on the graph. And here we just present 4 representative methods have been extensively using in the previous literature. The first one called the random walk algorithm. Essentially, you try to generate a random path so that people can obtain a statutory distribution over all the graph nodes. This has been extensively used for the application, for example, to compute the semantic similarity of text or to perform the name disambiguation task. The graph clustering algorithm has also been using for the text clustering. For example, once we formulate the text graph, people can either leverage, for example, the spectrum clustering technique or random walk clustering or mean cut clustering to do the text clustering task. Graph matching algorithm can also be using for the text entailment task that essentially try to compute the similarity between 2 graphs that is constructed from the hypothesis text and the text. The label propagation algorithm is also have been extensively used that essentially try to propagate the label from the label data point to the previously unlabeled data point. And so that we can use them to, for example, for such applications like water sensor disambiguation or sentiment analysis. For the more detailed graph-based, conventional graph-based method for NLP, we referring introductory to attendees to Mahasa and Radev graph-based method for NLP book. Okay, so we have been talking about a lot of conventional machine learning technique. Now let's talk about the modern technique, deep learning on graph. And we will talk about the foundations, and then we will talk about what's the popular model today. Let's first look at machine learning life cycle. Okay, so I believe most of people will have experience in the machine learning. And we know that the most important part is the feature learning. Okay, before the deep learning, so people have been spent a lot of time to do the feature engineering, because that is very, very important to convert the raw text into a very useful structure feature matrix. So as a rising of the deep learning, so we have intended to automatically learn the feature so that we can feed that to the learning algorithm into the model, and then we using downstream tasks to to update our representation and then to solve the downstream task. For the feature learning in the graph, it's the same idea. So our goal here is try to design an efficient algorithm so that we can learn a representation for each of the graph node. As shown in this figure, so I will take an input that is graph input, and here we'll try to learn a function f, such that the function f can translate this, transform this graph node v to this latent space. And in the latent space, we can use a vector to represent the graph node v. And sometimes we also call it embedding. Now let's talk about the foundations of the graph neural nets. Okay, so here we'll talk about two parts. One is how to learn node embeddings, other one how to learn a graph level embeddings. The learning process of the node embedding essentially is to take a graph input A is the adjacent matrix and the input node embedding, and then to generate an updated node embedding. And this learning process is also called graph filtering. And I can see that the graph filter operation become very important. Based on the type of the graph filtering, we can generally categorize them into 4 different groups: spectrum-based method, and the spatial-based method, attention-based method, and recurrent-based method. We'll talk about this different variant of the graph neural in detail in the later slides. So one thing we have to mention here is that graph filtering operation don't change the structure of the graph. It's only updates the node embedding. So that means that if we want to learn the graph level embedding, we have needed some other operation. This is we introduce the pruning operation. The pruning operation here is try to take the input graph and input the node embedding, and then to generate a smaller graph with the few node, and also to generate a new node embedding. Conceptually, we can cover them into 2 different groups. One is called flat group pruning operation, other one called hierarchical group pruning. So the flat group pruning probably is most used operation in most of the NLP application. For example, you're very familiar with like mass pruning, average pruning, or mean pruning. Okay, but people also try to develop more advanced methods. For example, in the hierarchical graph pruning, they tend to leverage the technique called the coupling technique, so that they can learn the representation for each of the graph in different layer, and then they can concatenate the different layers graph representation to formulate the final graph representation. So before I introduce the popular graph neural nets, so I would love to introduce very basic model to illustrate how graph neural nets works. Okay, so the key idea here is try to generate a node embedding based on the local neighborhood. As shown in this figure, let's assume that A is our target node. So in order to learn the node representation for A, we need to learn its context information. So what's the context information in graph? Essentially, it's its neighborhood, right? So for A, so its direct neighborhood will be B, C, D. And for each of the node B, C, D, they also have their own direct neighborhood. So that's how we formulate this computation graph. And intuition, we can see that the network neighborhood definitely will define a computation graph. And indeed, then each node will define the unique computation graph. And based on that, then we can design a neighborhood aggregation function so that we can have, in a different layer, we try to aggregate the different context information to formulate, to generate a new node embedding. So for example, in the first layer, typically we have an initial node attribute. And conceptually, it could be arbitrary depth for this graph neural nets. But in reality, it's only have a few layers. It really depends on the different variant graph neural nets. So how to develop a deeper graph neural nets is essentially a very active topic in the graph neural nets domain. But as we can see here, right, once we have the aggregation functions, then we can aggregate the node embedding from input side, and then to generate update node embedding, and then we can learn the representation for each graph node. So here is an overview for the graph neural nets model. So in the first step, we have to define a neighborhood aggregation function. And once we define that, then we can easily learn the graph representation for each graph node. And later we can define a loss function based on the embedding I've learned so far, and then to perform the segment results learning. So regarding the training, we can train on the set of the node. And here we can formulate a batch of the computation graph. And finally, we can generate the embedding for the node that we need. So the interesting part is that, so because we learning the aggregation function, we don't really learn a parameter for each individual node. So even for the node that we never trained before in the testing phase, we can still generate the embedding for the node that we never see. Okay, so now let's give a very simple aggregation function. We assume that we're using average function. Okay, so now we try to average a neighborhood information and apply a neural network. And we can see that, so then we just average a messaging from the neighbors, and then we can propagate the message, and then we learn the representation for each of the node. And so this is basically the math behind this message parsing process. So initially, we only have a node, an initial attribute, and then we can transform that into the latent space, and then we average the labels the previous layer embedding to generate called message, and then we can fuse this information with the embedding from the previous layer, and then we can apply a nonlinear transformation to generate the current node embedding. So, okay, so now it's a quick summary about this key idea. Okay, so very simple example to see that, so the key idea of the graph neurons that we can generate a node embedding by aggregating the neighborhood information. The good thing about that is that it's allowing for the parameter sharing in the encoder. It's also allowing for the inductive learning, as we mentioned before. Okay, so now let's go to more advanced models. Okay, so this is all the popular models that is today in the graph neural nets domain. So we are based on the type of the graph filter, we have been divided them into 4 different groups. The first group is called the spectrum-based graph filter. Okay, so the representative method is called the GCN, graph convolutional network. And the second group is called the spatial-based graph filter. So the representative method is called the message parsing neural network and graph sage. Later, people also invented the attention-based graph filter. So the representative method here is called graph attention network. And finally, it's recurrent-based graph filter. So the gated graph neural nets. So we will talk about each of the group in detail in the following slides. Okay, the first one, graph convolutional neural network, GCN. So the key idea here is try to apply spatial convolution on graph, which can be defined as an application of the graph signal input xi with a graph filter that being parameterized by the theta in the Fourier domain. So the U here, as shown in this equation, essentially is an eigenvector for the graph Laplacian. Okay, as you can see that, so if we perform a full eigen decomposition, it will be very expensive if matrix is large. So later people proposed to use a chip-shape polynomial to accelerate this process. But it's showing promising result, but not powerful enough. So in the graph convolutional neural network paper, they have been derived this first order approximation, essentially to leverage the Taylor expansion and only keep the first order information. Although it's a rough approximation, but have been showing that it's fast and powerful. So however, it's not stable if we just compute the computations through these equations. So this is the equations I'm talking about here. Okay, and finally, they have been applied this real normalization trick, and in order to stabilize the numerical computation. Okay, so GCN is most cited paper in the graph neural domain, have been widely used in many NLP tasks. For example, test clarification, question answering, text matching, topic modeling, information interaction. So another group is a spatial-based method. Okay, here we introduce two different methods. The graph, the key idea for the message parsing or the spatial-based method is try to treat the graph convolution as a message parsing process. So as shown in this equation, right? So in the first one, NPNN, so essentially they try to define two functions, update function and aggregation function. For aggregation function, it's used to aggregate the node and edge embedding, treat them as a message, and later use this message to combine with the embedding from the previous layers, and then use this update function to generate the updated node embedding. So this is very generic framework. Okay, so can be used to unify many different graph neural variants. However, as you can see that, so it could be very expensive if the number of the neighborhood of a node are large. So in order to address this significant computation bottleneck, so people later have been proposed called the graph stage. The graph stage is try to perform the sampling to obtain the fixed number of the neighborhood, so that we can only need to aggregate the certain number of the neighbors, so that you can generate a message and then to fuse with the previous iteration of the node embedding. Another good thing about doing sampling is also can help to reduce overfitting problem. So this is one of the big reasons why the GCN can only have a few layers, because the GCN essentially try to aggregate all the neighborhood. And here is also help to reduce overfitting as well. So the MPNN and graph stage method have been also widely used in many NLP tasks. So for example, in the knowledge graph, information interaction, and semantic parser. So the third group is called attention-based method. So the key idea here is try to dynamically learn the weights. For example, could be attention score on the edges when we perform the message parsing. So this is very reasonable, right? Because so in all previous method, they don't really consider the importance of each node. But in reality, the contribution of each node to the final node embedding, this node will be different. So this attention here can help to learn the importance of each node. And the way we're doing that is through this self-attention module. So this is essentially inspired by the transformer, the self-attention module, that uses multi-head self-attention to compute the weight, and then can perform the weighted sum of the node embedding in order to compute a better updated node embedding. And in the intermediate step, so you just keep all the layers, and finally you will average them to get the final node embedding. GAT is probably the second most used method in today's literature. Okay, have been widely used in many NLP tasks. For example, test clarification, QA, knowledge graph, information extraction, and semantic parser. So the last group of the methods called recurrent based method. So the representative method is a gated graph neural nets. Key idea here is try to using the gated recurrent unit while taking into account the edge type and the direction. So I will show in this equation. So they take the raw input, the node attribute as input, but because the different node may have different lengths of the attribute, so they use a zero padding in order to make all the graph nodes have same length. And a little bit different from all previous methods is that so it consider incoming, outgoing edge information. So this method can naturally deal with the directed graph, not like GCN. It's not really can be used for the directed graph without any modification. It's only designed for the undirected graph. And once we get the message information for A, and so then we can apply the gated recurrent unit to fuse the information together to generate a new node embedding. So gated graph unit is one of the earliest modern deep learning technique for the operating on graph, and it has been using in quite a few NLP tasks. For example, semantic parser, machine translation. Okay, so this is our roadmap for our DLG4NLP. So we have been, briefly introduced why we try to study the deep learning on graph for NLP. We have been introduced the conventional machine learning method for NLP. We have been also briefly introduced the several popular model in the graph neural domain, so that will give you enough background knowledge. So for the next part. The next part will be the deep learning for NLP, the key foundations. Essentially, it's considered for the 4 different parts. First, we will talk about the graph construction, and then we'll talk about graph representation learning, and then will be a very important branch is the graph-based encoder-decoder framework. And finally, we will using all different kind of NLP application to illustrate the power of the graph units for these NLP applications. And back to the graph construction. So we will talk about mainly talk about 2 different construction approach. One is called the static graph construction, and where we will introduce more than 10 different ways to leverage the domain knowledge to create a graph. And then we'll talk about the dynamic graph construction. This is not less popular approach, but it's a very important approach in our opinion, because it don't really require any domain knowledge. And then we will also naturally to think about that is any way we can, to combine the static and the dynamic graph construction to generate a better graph. Once we have a graph, right, so we have to select the best graph representation learning technique to solve the problem. So here it really depends on the graph type. If graph is an undirected graph, or it's a directed graph, or it's a multi-relational graph, or it's a heterogeneous graph. And based on the different graph type, so we will select the different graph representation learning technique. And finally is that, so we will introduce a special group of the technique, this graph-based encoder-decoder framework. We will talk about why we try to study that and what's the popular model here. Here we will introduce the graph-to-sequence model and graph-to-tree model. And finally, it's all these applications. Okay, so once we finish that, so we will talk about our just I mentioned before, Graph4NLP library. You will have a demo session there to learn how to use the code. And finally, is talk about the future direction. And that's all for the introduction part. So any questions so far? Okay, if we don't have any question, the next part will be our foundation part for our DLG4NLP. Now it's your follow.
Sure, thanks, Nlp. Let me share my screen. Can you see my screen?
Yes.
Yep. Okay, then I'll go ahead. Hello, everyone. My name's Yu. I'm a research scientist from Facebook AI. I'm very happy to introduce our next topic, which is graph construction for NLP. So as we previously introduced, there are three typical ways of representing text, which are bag, sequence, and graph. Among all the 3 approaches, graph has the strongest representation power because it can capture rich and diverse information about the text. So we know that different NLP tasks require different types of text, such as syntax, semantics. And in the meanwhile, different graphs capture different aspects of the text. Therefore, how to convert text to graph is an important yet a challenging question, which really depends on what aspects of the information we want to capture in a text graph. In general, we group variance we group variance graph construction approaches into two categories: static graph construction and a dynamic graph construction. So we will introduce each of them and summarize their properties next. So note that the primary goal of graph construction here in this tutorial is to achieve good downstream task performance. So let's first talk about the static graph construction. So it aims to convert the raw text to a graph where text can be like sentence, paragraph, documents, or corpus. And it's usually conducted during the pre-processing step by augmenting raw text with various domain knowledge, including like syntax, semantics, topics, concurrence, word knowledge, and so on. And many of them are actually quite application driven. Okay, next, the first static graph construction approach we are going to introduce is a dependency graph. So dependency parsing is widely used to capture the dependency relations between different words in a sentence. For instance, given a sentence, are there other jobs outside Austin? So one can apply a dependency parsing tools to convert it to a graph like this. So, but what if we have like multiple sentences in text? So one common way is to add additional sequential edges between nodes so that we can connect multiple dependency graphs in a paragraph. So besides, it also resolves sequential information in raw text, which can be helpful in some application. The next approach we will introduce is a constituting graph. The constituting graph is able to capture phrase-based syntactic relations in a sentence. For instance, given the same sentence, one can apply constituting parsing tools to convert it to a graph. So due to the same reasons, one can add additional sequential edges between nodes to reverse the sequential information in the raw text. The AMR graphs are widely used to represent the high-level semantic relations between abstract concepts of text. Different sentences that are semantically similar may share the same AMR graph. So given a sentence Paul's description of himself, a fighter, one can apply AMR parsing tools to convert to a graph. The IE graph aims to extract the structural information from text to represent the high-level information about entities and their relations. So given the input text, one can apply IE tools to convert it to a graph, which contains entities such as Seattle's as nodes and relations such as attended as edges. Core reference resolution is usually conducted to group entities referring to the same concept to a single node. Like here, Paul, he, and renowned computer scientists refer to the same person. That's why we can group them to a single node. The knowledge graph stores word knowledge about entities and their relations. Given a question, who acted in the movie directed by the director of Some Mother's Son, one can first identify the topic entity of this question, which is Some Mother's Son, and then extract a subgraph from a knowledge graph, which surrounds the topic entity and hopefully contains the entity answer entities of this question. A topic is a subject that text is about. So one can find the connections among multiple paragraphs or documents by connecting them to a shared set of topics. Another way to find the connections among texts is to compute their pairwise similarity scores. And one common way to do that is to compute the similarity score is to first embed the text into some vector representations such as TF-IDF vectors, and then compute their pairwise similarity in the embedding space. So in order to capture the word co-occurrence information, one can regard the co-occurrence matrix as an adjacency matrix, and then construct a graph containing each unique word as a node, which is corresponding to the adjacency matrix. Some logical forms such as SQL query can also be naturally represented as a graph, which well captures the relations among variance objects. There are also like variance application-driven graphs which augment the text with rich information, and they are typically tightly coupled with the specific NLP tasks, like this one I show here. So as we are already seen, static graph construction operates by augmenting text with rich domain knowledge during pre-processing, including syntax, semantics, topic, concurrence, word knowledge, and so on. For each type of domain knowledge, so there are various types of graphs we can construct, which usually depend on the specific application. So as we will see in the application part of this tutorial, these static construction approaches are widely used in various NLP applications, such as natural language generation, reading comprehension, semantic parsing, machine translation, and so on. So next, we will introduce dynamic graph construction, which shares the same goal with static graph construction. Unlike a static graph construction, which is performed during pre-processing, dynamic graph construction operates by jointly learning the graph structure and the graph representations on the fly. The ultimate goal is to learn the optimize the graph structures and the representations with respect to certain downstream NLP applications. So we summarize the typical dynamic graph construction pipeline as follows. Given a set of data points which can stand for various NLP elements such as words, sentences, and documents, we first apply graph similarity metric learning, which aims to capture the pairwise node similarity in the embedding space and returns a fully connected weighted graph. Then we can optionally apply graph specification tools to obtain a sparse graph, which can bring some benefits in some scenario. So if the input data is instead of data points, but an intrinsic graph containing edge information, one can also optionally combine the intrinsic graph and the learned implicit graph to form an augmented graph. The output graph will be consumed by a subsequent GNN-based module to learn graph representations and predict outputs. So next, we will introduce each of 4 dynamic graph construction techniques, which we summarize from the existing practice of its applications in the NLP field. So these includes graph similarity learning techniques, graph classification techniques, combining intrinsic graph structures and implicit graph constructions, and learning paradigms. So the idea of graph similarity metric learning is to compute the pairwise node similarity in the node embedding space and obtain an adjacency matrix based on that. So it can enable inductive learning because once the similarity metric learning is finished, one can apply it to unseen nodes to learn a graph. This is important for many NLP applications because we want to learn a new graph for each new text example. Variance metric functions have been proposed by previous works. We group them into 2 categories: node embedding based similarity metric learning and the structure-aware similarity metric learning. For node embedding based similarity metric learning, we are given a set of data points and their vector representations and apply variance metric functions to learn pairwise node similarity. The output is the weighted adjacency matrix, which is corresponding to a fully connected weighted graph. Common metric functions include attention-based and cosine-based functions. So let's talk about attention-based metric functions first. So in variant, here I show we see a variant of such a metric function. So in variant 1, here V1 is a node embedding vector, and U is a non-negative weight vector learning to highlight different dimensions of node embeddings. In variant 2, here W is a learnable weight matrix which maps the node embedding to a latent space so that we can learn the pairwise node similarity in that latent space. And ReLU function is used here to enforce the sparsity of the similarity matrix, which can lead to more sparse graph. So in both variants, dot product is used to compute the pairwise node similarity. So let's see an example of cosine-based metric function. So here, WP is a weight vector associated to the piece perspective and has the same dimension as node embeddings. Now we are doing element-wise multiplications here. So intuitively, SIGP computes the pairwise cosine similarity for the piece perspective, where each perspective considers one part of the semantics captured in the embeddings. So once then one can average like multi-head similarity scores to increase the learning power of magic. So this is kind of similar to the idea of multi-head attention employed in transformer-like models. Now let's talk about another way to design a similarity metric learning function, which is structure-aware similarity metric learning. So unlike the node embedding-based metric learning, this metric learning approach, in addition, considers the existing edge information of the intrinsic graph when it's available. So let's see two example metric functions. So here's one and here's the other one. So in these two variants, attention-based function is applied, and notably, edge embeddings of the intrinsic graph play an important role in learning the implicit graph structure. So that's the key difference in comparison to the non-embedding-based metric learning function. So far, similarity metric functions learn a fully connected graph. However, a fully connected graph is computationally expensive and might introduce noise. So we might want to enforce sparsity to the learned graph structure to obtain a sparse graph by leveraging various techniques as we list as follows. So let's introduce each of them now. So for KN style sparsification for each node, only the K nearest neighbors, including itself, the node itself, and the associated similarity scores are kept, and the remaining similarity scores are all maxed off. As a result, we can get like a sparse adjacency matrix. For epsilon neighborhood sparsification, those elements in the similarity metric, which are smaller than a non-negative threshold epsilon, are all masked off. So we can also obtain a sparse adjacency matrix by doing this. So besides explicitly enforcing the sparsity of the learned graph by applying like certain form of thresholds, sparsity can also be enforced implicitly in a learning-based manner. For example, we can apply certain form of graph regularization to the learned adjacency matrix in order to enforce sparsity. So the intrinsic graph typically still carries rich and useful information regarding the optimal graph structure for the downstream task. So some recent works are proposed to kind of combine the learned implicit graph structure with the intrinsic graph structure based on the assumption that the learned implicit graph is potentially a shift like substructures from the intrinsic graph structure, which is actually supplementary to the intrinsic graph structure. So as a result, we might be able to obtain even better graph structure by also take advantage of the existing information of the initial graph structure. So one common way to do this is to compute a linear combination of the normalized graph Laplacian of the intrinsic graph structure and the normalized adjacency matrix of the implicit graph structure. And here we can use various ways to normalize the implicit adjacency matrix like graph Laplacian or like raw normalization operations. So now let's talk about some important learning paradigms for dynamic graph constructions, which have been explored so far. So most existing dynamic graph construction approaches for GNNs consist of two key learning components, graph structure learning and graph representation learning components. So the most straightforward approach is to jointly optimize the whole learning system in an end-to-end manner towards the downstream prediction task. So actually, most of the dynamic graph construction approaches follow this learning paradigm. Another strategy is to adaptively learn the input graph structure to each GNN layer to reflect the changes of the intermediate graph representations. So this is kind of similar to how transformer models learn different weighted fully connected graphs in each layer. So here we can also learn adaptively learn different graph structures at each GN layers based on the intermediate graph representations. So that's the key idea of this learning paradigm. So unlike the above two learning paradigms, recent work proposed an iterative graph learning framework by learning a better graph structure based on better graph representations, and in the meantime, learning better graph representations based on the better graph structure in an iterative manner. As a result, this iterative learning paradigm repeatedly refines the graph structure and the graph representations towards the optimal downstream performance. So far, we have introduced various dynamic graph construction techniques, including the graph similarity metric learning, graph specification, combining intrinsic and implicit graph structures, and the various learning paradigms. So one might ask, like, how is static graph construction compared with dynamic graph construction? Which one is better? So let's first talk about the static graph construction. So the biggest advantage is that the static graph construction can easily encode rich prior knowledge in a graph, which can be very helpful for certain NLP applications. But this can also become a downside when it's expensive or not durable to obtain such extensive domain expertise. For example, for some low resource languages, we might not have rich prior knowledge to utilize. Besides, static graph construction is error prone due to noisy or incomplete graph, and therefore is often suboptimal. Due to its disjoint graph construction and the representation learning nature, it can also lead to error accumulation. Compared to static graph construction, dynamic graph construction is quite new and has not been extensively studied in the DLG4NLP area. Its advantages include requiring no domain expertise and joint learning of graph structures and representations. So currently, it also has some disadvantages, such as the scalability, because we need to learn like pairwise node similarity, and also the explainability. So which actually these are also like good future directions in this dynamic graph construction topic. Now it comes to the question like when to use which. Based on our study and practice, it's best to use a static graph construction when we have domain knowledge at hand, which fits the specific task and the domain knowledge can be represented as a graph naturally. For dynamic graph construction, here might be some reasons which we will consider if we want to look into the dynamic graph construction approach. So these reasons might include like if we lack of domain knowledge which fits the task or can be represented as a graph naturally, or the domain knowledge we have at hand is incomplete or might contain some noise, or we want to learn, even though like we have we can have we have like initial graph based on static graph construction approaches, but we might want to also learn implicit graph which augments the static graph as what we already like discussed when we talk about like combining intrinsic and implicit graph structures. So so we think that these are some reasons we want to consider when we try to make a decision on like which graph construction approaches to use for a specific application. Okay, so that's all for the graph construction for NLP part. is there any questions? Maybe we can take a few like quick questions here. All right, so if there's no question, maybe we can reserve it later. Now I will move to the graph representation learning for NLP part. So let's briefly recap on the DLG4NLP pipeline. So given a graph, we will need to decide which GNNs to apply for graph representation learning. So we will try to help answer this question in this part of the tutorial. So let's first review some definitions on various types of graphs. So these concepts are important since we will mainly depend on the graph types to choose which GNNs to apply for a specific application. So in general, we have three types of graphs, including the homogeneous graph, multi-relational graphs, and the heterogeneous graphs. So for the homogeneous graphs, the definition is that the number of node types is 1, and the number of edge types is 1. As for multi-relational graphs, the definition is that we only have single node type, but we can have multiple edge types. And as a definition on heterogeneous graph is that we need to have like we have like multiple node types, but we do not have any restriction on the like number of edge types. So in general, like any graph can be grouped into one of these three categories. So let's first see the overall roadmap on which GNNs to use given a graph. This works like a decision tree actually, so which we summarize to help you make this decision. So in short, we will decide whether to apply homogeneous GNNs, multi-relational GNNs, or heterogeneous GNNs based on the specific input graph types. So we will decompose this roadmap in this part of the tutorial and introduce them the corresponding GNN types. So first, let's talk about the homogeneous GNN. So the question is when to use homogeneous GNNs. So given a graph, if it's a we can use the definition of the homogeneous graphs to determine like if it's a homogeneous graph. If yes, then like we can simply apply homogeneous GNNs here. If it's not, then we might want to convert the non-homogeneous graphs to the homogeneous graphs so that we can like straightforwardly apply homogeneous GNNs here. So we will introduce one specific common technique to achieve this next. And there are various homogeneous GNNs, and many of them have been covered in the introduction part of this tutorial, like GCN, GAT, GraphSage, and the GGNN. So given a non-homogeneous graph which contains various edge types, so we can leverage Lavie graph conversion to convert it into a homogeneous graph. Then we can simply apply homogeneous GNNs to the resulting graph. So the key idea here is to regard each edge in the original graph as new nodes, and then connect original nodes and the new nodes. As a result, we will get a bipartite graph, where there's only a single edge type. So we know that edge direction is also very important. Let's think about the success of BiLSTM and the BERT models. So given a directed graph, we might not be able to directly apply some homogeneous GNNs, which will lead to edge direction information loss. So common strategies for handling directed graphs include like one, we just simply do message passing only along the directed edges. Then we can apply GNNs like GAT and GGN, for example, to do that. So that's the simplest approach to do that, but that will lead to edge information loss still. And the other way to do that is, another way to do that is we can regard edge directions as edge types, which we will detail more in next slide. And the third approach we want to introduce here is to apply bidirectional GNNs, which can naturally handle the directed GNNs quite well. Okay, so let's talk about the second strategy we just mentioned, which is to regard edge directions as edge types. So the idea is quite straightforward. So there are typically like three types of edge directions. The default direction, which is the edge existing in the original graph, and the reverse direction, which is we can add reverse edges to each existing edge in the graph, and we can also add self loops to each node. So these are three types of edge directions, and we just simply regard them as three different edge types. Then we can apply multi-relational GNNs to encode this graph. And we will talk about like what are some multi-relational GNNs we can use later. We summarize the two variants of bidirectional GNNs. So this is the third strategy we just mentioned to handle directed graphs. So the first one is called bicep GNN. So bicep actually works quite similar to the famous BiASTM model. So we first run multi-hop backward and forward GNNs on the graph separately. Then at the final step, we get the backward node representation and the forward node representation. Then we just concatenate the backward node representation and the forward node representation at the last step, and then we get the final node representation. So and we see that it's quite similar to the BiASTM strategy. The second one we will introduce is called the bifuse GNN. So let's see each of the steps it will take. So first, we can run one hop backward and forward node aggregation separately at each hop. Then we can get the backward node aggregation vectors and the forward node aggregation vectors, and we can leverage variance node aggregation functions like average or like max to do that. Then we just at each hop, we just fuse the backward aggregation vector and the forward aggregation vector to get like fuse the vector aggregation vector for each node. Then at the last step, we just updated the node embeddings with the fused aggregation vectors. And that's how we can do bifuse GNN at each hop, and we can stack multiple GNN layers to have even powerful representations powers. So now let's talk about multi-relational GNNs. So when to use multi-relational GNNs? So given a graph, let's first like tell if it's a homogeneous graph. If it's not a homogeneous graph, then we can think about like whether we want to convert it to a homogeneous graph. That's what we discussed before. If we don't want to do that, then we can tell if it has a single node type or multiple node types. If it actually has a single node type, then we know that it's actually a multi-relational graph. Then we can apply multi-relational GNNs to encode the graph. And for multi-relational GNNs, we can have various types of architectures, and we summarize the three common variants, which either including relation-specific transformation parameters in GNN, or include edge embeddings in the GNN, or it leverages the idea of multi-relational graph transformers. So we will introduce each of them in the next few slides. So let's first talk about the first strategy. So RGNN is the most common variant, which works like this. So the key idea is that it introduced two key features. The first feature is that it applies relation-specific transformation to the, for example, the node feature transformation or attention weight to the GNN message passing process. so that we can explicitly encode the relation type information. And the second feature is that they aggregate node embeddings per relation specific subgraph, as we can see from this diagram. Like we have n relation types, and for each of the n relation specific subgraphs, we do node aggregation separately, and we apply relation specific transformations separately. So that's the key idea of RGNN architecture. So RGN actually can have like variants, can have multiple variants. We can apply the same idea to GCN, GAT, GraphSage, GGN. So let's talk about one example, RGCN here. So in order to that, we can apply relation-specific node feature transformations during the neighborhood aggregation. If we look at this equation, so the main difference, the main part here is that it applies relation-specific D by D learnable weighted matrix to the node features, and it aggregates the node embeddings per relation-specific subgraph. So for RGNN, it's actually good at doing like relation-specific message parsing and hence handle multi-relational graphs well. But it's actually expensive because we need to have a D by D transformation weighted matrix for each relation. And let's say if we want to apply multi-relational GNs to a logic graph, then that will be a disaster because we can have like maybe like thousands or like 10,000s of different edge types in a KG. So it's not quite practical to apply GN directly. So there are two common ways to address that, to avoid the over-parameterization issue and to reduce the model complexity. So the one way is the basis decomposition strategy, which regards the relation matrices as a linear combination of shared bases, which can be seen as a form of weight sharing between different relations. And then the second strategy is the block diagonal decomposition, which can be seen as a matrix sparsity constraint applied to the relation specific. So that's to first the type of GN iterations. Let's talk about second multi-relational GNs, which explicitly includes the edge embeddings in the GN message parsing part. And you can see that they are embedding EIJ introduced in this node aggregation step. And in the second variant, the key difference compared to the first variant is that it also updates the edge embeddings at each GN layer. So now let's talk about the third type of multi-relational GNNs. So we know that transformers can be regarded as a special class of GNNs. Currently learn and encode a fully connected graph via self-attention and each transformer layer. And it also shares many similarities with the GAT, which is a very popular variant of GNN. But it has some drawbacks. One of them is it fails to effectively handle arbitrary graph structured data. And we know that transformer has been widely applied to encode like sequential data and maybe like set data if we remove the position embeddings. But in order to handle graph structured data, the vanilla transformer is not quite capable of doing that. So that's why we people introduce the multi-relational graph transformer ideas here. It has two key features. One is it employs with structure-aware self-attention, which leverages the graph structure of the input data. And the second feature is that it respects variance relation types so that it can handle multi-relational graphs. So let's first see one example, which is RGAT-based graph transformer here. So the key idea here is that So there are two key ideas here. The first idea here is to apply a GAT-like mass attention functions in the node aggregation step. So that's the difference that's different to the vanilla transformer models, because in the vanilla transformer models, we do not have this graph-based master matrix, and the transformer considers like pairwise node similarities. And then the second feature here is it introduced the relation-specific learnable weight matrix, which has also been this idea has also been used in like RGN models. So the second multi-relational transformer model we've introduced here is the structure-aware self-attention-based graph transformer. And the key idea here is to introduce the edge embeddings to the self-attention mechanism, so that when we the graph structure of the input data can be respected when doing the self-attention learning. Now let's move to the heterogeneous GNNs part. So when to use heterogeneous GNNs? So given a graph, we can tell if it's a homogeneous graph, if it's not, and if we don't want to convert it to a homogeneous graph, and then we'll tell if it has like multiple node types. If it does have multiple node types, then we know that it's a heterogeneous GNN. Then we can apply heterogeneous GNNs to encode the graph. And in this tutorial, we will introduce one specific type of heterogeneous GNNs, which is based on the metal path idea. So the metal path idea. So here we have a diagram to demonstrate what is the idea of metal path. Let's say we have a graph which contains various node types like author, paper, topic, and we have also various edge types like author can write a paper can mention a topic, and paper can be published in a venue, etc. So we know that it's actually a heterogeneous GNN. And if we want to consider like what are some different types of paths between two author nodes, we can actually name a few. For example, for P1, it's author write a paper mention a topic is mentioned in another paper, and the paper is written by another author. Or we can say that the author write a paper, the paper is published in a venue, and the venue also published some other papers which written by some other authors. So this is how we can construct like different metal paths between a pair of node types. So that's the idea of metal paths. So for metal path-based heterogeneous GNNs, so below are the three key steps. So in the first step, we apply node type specific feature transformations to each node. And in the second step, we do node level aggregation along each metal path instead of like we do the node level aggregation in the whole graph in homogeneous GNNs, or we do node aggregation in each relation-specific subgraph in the multi-relational GNNs. So that's one of the key difference of the heterogeneous GNN. And in the last step, we do metal path level aggregation to get the aggregated vectors, which can be used to update the node embeddings. So that's the three key steps of heterogeneous GNNs. So I will pause here for a while to take some like quick questions if we have.
So Angel has a question on the chat. Would you like to speak up? Have some discussion right now or later?
Sorry, I can barely hear you.
So there's a question on the chat by Jason Angel. Jason, would you like to speak up or wait until later?
Sorry, weekly information.
Yeah, it seems like your signal is not very stable. Maybe we can continue the presentation, and then we will have a half-hour break. And during break, maybe we can take a Q&A question about that.
Okay, sounds good.
Yeah.
Yeah.
Okay. Sounds good to me. Yeah. So that's my part. And next, let's welcome Lin Fei to introduce the graph encoder decoder models for NLP. Yeah, let me stop sharing my screen.
Okay, so we have been discussed graph construction and different graph repetition learning technique. So one of the most important models is called encoder-decoder model. Is the one used in the NLP domain. So in this part, we will talk about the graph-based encoder-decoder model for NLP. So as we all know that, so the sequence model is extremely successful. It's originally designed for a machine translation problem, but later have been widely using for example, natural language generation, multi-form translation, information extraction. So for sequence model, essentially is take a sequence input and then to learning a mapping between a sequence input and a sequence output. But obviously the challenge is that, so if the input is not originally represented in sequence, then we have a problem there. And that means that the sequence model cannot deal with a complex structure, for example, graphs, because you have to convert the graph into the sequence input. And because the graph is a multi-film phenomenon, you really don't know which node you should start to convert graph as a sequence. In that case, that if you convert graph input to a sequence input, you definitely will lose information. So another strong reason to think about beyond the sequence model is that, as we mentioned a lot, so we have been seeing a lot of the hidden structure information, regardless it's the syntactic structure information or semantic information behind the word sequence. This is very useful that if we use that information to augment our current text sequence. So that motivates us that, so we try to develop a model that beyond the sequence model. So in this case, so we have been proposed this called graph to sequence model. So this model essentially is a generalization of the sequence model in a sense that, so it's an attention-based method to using graph encoder to encode the complex input side and then to decode as a sequence. So as you can see here, that so the graph encoder could be very flexible, right? So this is a generic framework. You can use any graph encoder. And specifically in this graph sequence model here, we have been using a bidirectional node embedding technique. So we have been explained that very well in the previous slides, that we will later show that indeed that is more powerful than the unidirectional node embedding. And for the sequence decoder, you have to generate a graph level embedding to summarize the whole graph and then to send to a sequence decoder. So attention mechanism is very important for this particular sequence decoder, as we all know, because if you don't use the attention mechanism, your sequence performance will be really bad. Okay, so we have been explaining this two different ways to do the bidirectional node embedding, by shape and by fuse. So I will skip these details and directly jump to the third part, the graph encoding. So once we learn the bidirectional node embedding for each of the graph node, we have to generate a graph level embedding to summarize the whole graph and use that as a context information to feed it to the decoder. They generally have two different type of methods. We can either use a pooling-based graph embedding. For example, we can use mark pooling or mean pooling or average pooling to generate a single vector that can summarize the whole graph. Or we can use a node-based graph embedding. In this case, we will create called super node. And this super node will be connected to every node in this graph. And then we just run this graph unit as a euro. And then finally, we were using the embedding of this super node and as a graph level embedding. So this definitely is a very interesting idea, but in reality, we have found that it's not as good as pooling-based method. Probably the reason is that when we create this super node, and this is actually an artificial node that we insert into an original graph. so that we actually modify the original graph structure. Therefore, the length of the final the length node representation is suboptimal. So once we get to the graph level embedding, so we need to feed that to the sequence decoder. And as we all know that the attention become very important in this part. For the attention part, so we just apply the graph level embedding to attend of each graph node, and then we can compute the attention weight. And once we have an attention weight, we can compute the context vector. So this is a very simple model, but I want to highlight that. So the attention here is a generic attention. That really depends on how we treat the current graph. So if a graph is undirected graph, of course, this attention, is a very simple attention mechanism. Will work well. However, if a graph, for example, is a multi-relational graph or is a heterogeneous graph, so then we may consider a more complicated attention mechanism so that we can make full use of the graph structure. So we will talk about this attention variant, in the following slides. So, but once we're doing that, so our goal here is try to maximize the local likelihood to predict the less word token, given the tokens that are already predicted and the input sequence. So here is kind of a simple task that to try to show that the graph sequence model really is perform very well. So we have two different tasks. One is, for example, text reasoning. This is kind of a baby data set. Baby data set is only designed by Facebook back to the 2015 to validate the reasoning capability of the deep learning model. Okay, and the other task that we have been using is called the shortcut path. Okay, so for both of them, they have a common similarity is that for both of them, we try to generate a path that from the original location to find the optimal path from the original location to the destination location. Okay, just for the baby task that we also need to understand this natural language. For the short path, we just give an original graph. Okay, so you can see that for both tasks, so if we use the LSTM-based method, that is a sequence-based method, then it's hard to really generate a good result. And if we're using other graph neural nets, that essentially is unidirectional node embedding, it can do the job well, but it's not as good as this graph sequence model that leverages a bidirectional node embedding. And for the short path task, so we can see that we have two different settings. One is using a small graph, okay, one is a large graph, because we believe that when the size of the graph increase, the model capability will decrease. So we compare with the STM-based method. In this case, it's fail miserably. And for the graph-based method, if we use a small graph, seems like all graph-based methods perform very well. But when we increase the graph size, we can see that the bidirectional node embedding indeed can capture a much better context information as an unidirectional. We have a further study about the effect of the bidirectional node embedding. So we can see that when we using same number of the hops, okay, the bidirectional node embedding indeed will converge much faster. So that's showing that have a better performance. But when we continue to increase the number of hops, right, that means that even for the unidirectional method, they are able to reach all the content information for this graph. Therefore, finally the performance is converged. Okay. Okay, so the graph sequence is definitely useful, but when, right? So we have been identified two different cases. The first case is that when the input are laterally or best represented in graph. So as shown in this figure, this is AMR graph. Okay, so one of the popular tasks in the NLP is called AMR to text. So that will take the AMR graph as input and try to generate a lateral language to describing what it's talking about in this AMR graph. So as you can see here, that if you use a sequence model, definitely you will miserably fail because you don't know how to, or not the best way to convert the graph as a sequence and then to do sequence. So in this case, the graph to sequence is a very natural model to tackle this problem. The second case is that we are able to using some hidden structure information. Many times, the hidden structure information we're talking about is some very useful domain knowledge that we have is behind the text sequence. And that's because the human language is a very high level symbol. It's not a simple symbol that don't have any meaning. Therefore, that so although it looks like a text sequence, but essentially it have a lot of the meaningful hidden structure information behind that. So use this kind of a domain knowledge to augment your kind of sequence definitely will help you to gain more knowledge about your input. So this is another way that we create a graph that you have been discussed a lot, different way to construct this graph. And that is a case study, so graph sequence model will work. So moving forward, so in less common task in the NLP, but where we try to learn a structured input-output translation. So just look at this table, okay? So for example, in semantic parser, so the input could be like, what job are there for job development who know C++? And the output will be, this answer, blah, blah, blah. This is a logic form, right? So as you can see that, so this structure output essentially is not a simple sequence. It can be formulated a more rich data structure so that it can better represent this output. Similarly, we can see that in the slightly growing interest application called math word problem. So the input essentially is kind of like a short description about mixed with a number and the word, and the student is required to understand this and then to write an equation to solve the problem. So you can see that so this math equation here is definitely not a simple sequence. It's how is a structure behind these equations. So in these two cases, so if we have been gain knowledge about our text input to translate that into a graph format, then we can think about that we are really talking about how to translate a structured input to a structured output. So that's why we call it learn a structured input-output translation. And so here we have give some example here, right? So we can, for example, using dependency path tree to augment, get a text graph. We can use a constitution tree to augment, get another text graph. And for the math equation here, for this equation, we can construct such a tree-like structure to represent this equation. And in this way, so that's why the motivation that while we try to learn a matching between a graph input and the tree output. And so there are potentially different way to do the tree decoding. So for a tree, right? So we can use the depth first search best method, try to decode the output. We can also using breadth first search based method to do the tree decoder. But both of them will have a different advantage and disadvantages. So we are tended to choose the second way. So that's why we propose this graph to tree model that we take a semantic parser as an example. So input will be a text sequence, and we're using dependency path tree to augment that to formulate a homogeneous graph here. And so once I have that, we are using our bidirectional node embedding algorithm to compute the bidirectional node embedding. And once I have that, we will use pruning operation to generate a graph level embedding to summarize the whole graph. And then we will feed that to a tree decoder. So in the tree decoder, it's very important to have an attention mechanism to find out, highlight what's the most important input that may contribute to the kind of decoding. Okay, so you can see that since the input graph here is not an Android graph, essentially it's a directed and heterogeneous graph because different nodes have a different type. Some of the graph node is from the original text sequence token. Some node is from the dependent path tree. Okay, so in this case study, so we have been try to using separate attention, try to perform this job, to attend the graph node that's with a different type. And in this way, we can get a better context vector and then to perform the decoding shown in the right-hand side. So the separate attention we're talking about here is we try to generate the context vector embedding based on the attention that we have been talking about before. And finally, we can compute the final attention hidden state by utilize all the information we have here, the context vector from the different node and also the current hidden state. So we have been showing this on a simple problem, massive water problem. And so this is a very small NLP applications, but they gain popularity in recent years. And we found that, so compared to the current state of art, we have two observations. First observation is that, so since we are fully consider the structure information in both sides, input and output, therefore that our approach is outperform all existing approach that is either based on the sequence or based on the water sequence. The second important part is the current massive water problem. They are tend to using some trick called like equation normalization. That essentially try to reduce the complex mass equation into the same format. For example, as we all know, right? So in order to solve a math problem, you can have many different person can come out different math equation to solve that. Okay, but if you normalize them into a single one, then it makes the learning problem much easier. But it's also break the original reasoning state that we want to learn how we solve this problem. But our graph tree model, because we don't use this kind of a trick, we are firstly to translate the original input to the output so that we preserve the original reasoning process. So here is some kind of visualization of this separate attention. So we can see that, so if we have attention based on the water node, indeed, so the translate output, it can highlight the important word from input side. And when we have attention to the structure node, that's from the either from the dependent tree or constitution tree, we can see that they also have their correspondence. So this is a very interesting visualization result. So showing that so the separate attention indeed is very important to the final performance. And so that's all for deep learning for NLP foundation part. And so we will have a half-hour break. But at the same time, you are very welcome to stay here and to ask questions. Also, we want to tell you that so in the second part, we will have a demo session. So if you want to prepare for demo, or you can run the following command to we will copy and paste this in the chat, and later we will lead you to see how to use our graph NLP library. And so you can try out to see that if it's working for your applications. And yeah, that's all for the first part of this tutorial. So any question?
So Nlp, there are a few questions on the chat. So maybe whoever asked a question, can you please unmute yourself and ask the question if possible?
So Jason said he has a mic problem. We'll have to read aloud his question if Jason is still here.
So you answered his question on the chat. Okay. Jason, if you have any follow-up questions, please use the chat. And then we have, I think, 3 more people. So you can request to unmute yourself.
Yeah, maybe people are just a little bit intimidated by the recording.
Okay, maybe we can read it out. Nlp, if you go to the chat, you can see the question. I think first question for your session is from Eduardo.
From
so
where?
Talk about is this a super node similar to the CLS token?
This is a little bit different. So this is conceptually it seems like they do a similar thing, but the supernode here is you can artificially add that and connect to the all the node. Oh, you are talking about the transformer, right? That's right. They're very similar, actually. They're very similar. Yes, you have this basically it's a token, right? You connect to the every other token, and then later you use that as a representation for the whole either sequence or whole graph. It's a similar, but the difference is that if we add the supernode into the graph structure, because for graph neural nets, so typically you already have a graph structure there, and if you add a supernode, then you will essentially introduce noise to your original graph topology, and that may cause problem to the learned node embedding. And so in our experiment, we have seen that, so I didn't show you in these slides, is that pruning-based method that will outperform the supernode-based method, because the pruning-based method essentially didn't create any false topology issue as the supernode approach. Hopefully that answers your question. And second question, if graph contain multiple layers, then in which layer is supernode inserted? Oh, so the supernode essentially is inserted in the original graph. So as we mentioned before, so even though that you have a multiple layer of the graph, but you take a graph input A, right? So that A, if A is already changed, then for the every layer, the A will be replaced by a new A that will contain the supernode. Okay, and intuition, why constitution paths perform much better than dependency paths? One potential reason is that the constitution path seems like can have a more complicated, can capture more complicated syntactic structure of sentence, and dependent path is more flat. So we don't know what the exact reason of that, but so this may, because it's a flattened graph structure, that means that it may not capture as more information as a constitution parser. So that's probably partially explains that why the constitution parser is performed better. But in reality, actually, yeah, we have compared them because sometimes it could be like dependent parser perform better. So it's a more empirical explanation.
So there is also an earlier question from Radip about if the graph contains multiple layers, then in which layer is a supernode inserted?
If multiple, I already answered the question. Yeah, okay. So since the supernode is essentially inserted to change the original graph, that essentially means that the adjacent matrix A is changed. So therefore for every layer, when you're doing the graph filtering that I introduced before the operation, so it's always have that supernode inside. So it doesn't matter how many layers do you have. How do we do batch processing on graph? Maybe you can answer the question.
Yes, so the question is like, how do you do batch processing on the graph? So I think this question is more broadly related to the broader deep learning on graphs techniques, not limited to the NLP field. I think there are many literatures on like efficient GNNs, which based on which leverage the sampling based ideas when training a GNN. For example, like you can do layer-wise sampling, or you can do subgraph-based sampling, where in each batch you just sample a subgraph from the whole graph based on some criteria, and then you train the GNN parameters on the subgraph at each batch. So I will recommend you to refer to those efficient GNN papers for more details regarding this.
Yes, So Jason have asked question, does a graph NLP library offer some computation of the Porter model for graph scenario? Yes, so we haven't go there, but when we go there, we talk about that. So our overall architecture, our graph for NLP library. So where you will see that, so sorry, where you will see that, so we also have built on runtime library Hugging Face to provide the broad pre-trained embedding. And that where you will see that, so how we combine the power of the graph neural nets with a transformer or BERT embedding. Yeah, you will give some detailed coding demo there. So Zhao Feng asked a question, for dynamic graph construction, do we usually have intermediate structural supervision, or is it only training signal coming from the downstream nodes? If it's later, do we need to use a latent structure optimized technique to combine non-differentiable of discrete structural decisions? Yu, this is your part. Maybe you can answer the question.
Sure. Yeah, I think that's a good question. So, so in most dynamic graph construction papers, actually, people did not use the intermediate structure supervision for several reasons. Reason one, like we do not have the ground truth graph structure which is best for the specific downstream task. So the second question is that the second reason is that we actually want to. So we do not have the supervision yet, but we actually want to learn the best graph structure, and our criteria is that whether we can achieve the great performance on some downstream task. So the short answer is that we do not have such supervision signals. And I think and also there are like second questions I think mentioned here. If it's a latter, do we need to use latent structure optimization techniques to combat the non-differentiability of the discrete structure decisions? That's also a very great question. So for the dynamic graph construction techniques I presented in this tutorial, there's no such non-differentiability issue, because either when we do this like graph specification operations, like either we do KN style specification operation or epsilon neighborhood style specification operations, we actually still keep the differentiability of the learning system. So it can still be trained in an end-to-end manner. But there are some dynamic graph construction approaches which are not exploited very much in the NLP field, but in the more broad like ML field, there can be some non-differentiability issues which can be handled by some other techniques like the variation inference approaches or like RL-based approaches.
So there's some question regarding, can we using model from graph NLP with a trainer class of the FQ face? Maybe you can answer the question.
Yeah, that's a great question. So currently, as we will introduce in the later part of this tutorial, like our graph NLP library actually has the interface to the Hugging Face transformer-like models, but we currently do not leverage their trainer class. But I think that could be something we will consider in the future.
Yeah, Jason, you are welcome to submit a pull request so that we can address them one by one in our later development. So that's one. What's the advantage of the graph-based NN compared to the pre-trained transformer? So yeah, maybe I can answer the question. So so one thing I want to highlight here is that I don't think the graph neural nets is a competitor of transformers. That's because first of all, the graph transformer essentially a specialized graph neural nets, and second thing is they can be combined quite effectively. For example, the power of the pre-trained transformer is usually from the embedding that we have been learned through a very large corpus. Okay, and so then we can leverage the, for example, pre-trained BERT, okay, to generate the contextualized word embedding. And then we can build on top of that, have a graph neural nets take that as an input, and using graph neural nets to generate or to update the graph node embedding, so that we can get even better result. So that's the way that I try to give an impression to people that how we compare the graph neural nets and the pre-trained transformer. So can you expand? Sorry, I cannot see that. Can you expand the condition mentioned in the iterative learning? What's the metric to tell when the graph learner GN and dunking tasks are fit? You want to answer the question?
Sure. Yeah. So for this question, can you explain like the condition mentioned in the iterative learning? So yeah, I think there could be various options in terms of the stop condition. And in one of our newest papers, like titled IDGL iterative deep graph representation graph learning. So we actually designed one specific stop condition, which is to measure the difference between the adjacency matrix at consecutive iterations. If that difference of the adjacency matrix is not small enough, then we can stop the iteration process. And we found that it works quite well in practice. But there could be other effective like conditions.
Yeah. Basically, how to stop this iterative learning process for joint learning and graph neural nets and the graph learner. I think it's a very active area. So in you and I, our previous newspaper, I think we just presented one solution, but definitely I believe that there are many other solutions that people can try. And Jason have asking a new question. Do you know any pre-trained language model that can use a graph as input? So Jason, you have been, this is a great question. So this actually is one of the future directions that I will talk about later when we conclude the slides. Yeah, so currently the answer is no. Okay, simple answer is no. And but in both domain, they have a pre-trained language model. They have a pre-trained graph neural nets. Okay, but haven't seen people try the pre-trained language model that use graph as an input. And I believe this is a very interesting direction. And we will discuss a little bit more when we talk about in the future direction. So can we ask question, GN more computationally intensive than other AA, such as transformer, even though the number of the parameter is almost the same? So I don't think so. I don't think the graph neural nets is more computationally intensive. So transformer essentially operate on the fully connected graph. Fully connected graph actually is have a quadratic complexity. Okay, so in that sense that so the graph neural nets essentially is really depends on what kind of graph neural we are talking about here. So in the worst case, the graph, for example, GCN, you take A as the original A as an input, then if it's dense matrix, then the operation cost will be the quadratic complexity. That is a matrix vector operation. Okay, but if a graph itself is sparse, then you can reduce the compute complexity compared to the transformer, because transformer only can take the fully connected graph. And more importantly is that so in other graph neural nets, for example, this is also regarding how to scalable graph neural nets computation. Then like GraphSage is that essentially only sampling the neighborhood of a particular node. So that means that you don't really have to operate on the every label you have. So that even reduce the computation cost. And this is a very active area. So people have been trying a lot, how to scalable graph neuronets. But in general, I think the graph neuronets could be more efficient than a transformer because transformer have a quadratic complexity. But I have to admit that the transformer today is also have a lot of people try to doing, for example, light transformer or more efficient transformer. The way people try to scale the transformer computation is very similar to graph neuronets in the sense that they try to use like a low rank approximation or using some. This is also have a connection with another domain. It's color method and color approximation method that have been extensively studied in the past several years. So they have been borrowed many ideas from how to scale the color method into a large matrix. But this is a very active area, and there are many papers have been produced. So R asks question, could you discuss a little bit more about the sparsity? Why is required? How can we optimize the measure if we have an accurate number of the model distribution represented once we have formed a dynamic graph? You want to answer the question?
Yeah, I think that's a really great question. So yeah, so as I introduced in the tutorial on like why the motivation of doing like graph specification. So there are a few reasons which I can summarize here. So one reason is that we want to doing fully applying GN to fully connected graphs is quite expensive. Like the complexity is at least n squared, but if we can have a sparse graph, then the time complexity can be reduced to like almost to the number of edges, which is much faster. And the other reason is that fully connected graphs can contain noise, like we can have some very small weights learned by the semantic metric, which can contain noise. But if we just kind of mask off those very small weights, then maybe we can have more robust results. And the other reason is that it might also help to kind of avoid over smoothing issues of GNNs. And for the second part of that question, how can we optimally measure if we have accurate number of modes of distributions represented once we have formed a dynamic graph? So I'm not quite understanding like what's the definition of number of modes here, or if we and what does that mean to a graph? Maybe
I think probably that means that
a little bit more on this.
Yeah, I feel that probably they want to ask that. So, how do we know the current sparsity of the graphs? The matrix sparsity is already enough to present.
Yes. Yeah. Yeah, I think yeah. So as I mentioned in the tutorial, like for the graph construction for NLP, for this specific topic, I think our ultimate goal is it's not to learn a like very explainable graph structure, but instead, in order to have optimal performance on the downstream task. That's even more true for the dynamic graph construction. So so I think really we want to measure its performance on the downstream task performance. Yeah. So that's my understanding.
So Jason asked a question, mentioned, Chris Manley mentioned in his recent talk, the LM already know or infer the syntax behind the sequence. That is captured by a transformer, for example, attention between word. So that means that probably we don't need to add implicit graph structure in order to improve that. So I have a similar chat with Manny back to the 2019 in the NAACL conference. I believe what he mentioned here is try to explain why the transformer type of embedding that is performance so great that that seems like it can capture this very shallow dependency between word token that is a similar. This is can capture the similar syntaxes that captured by, for example, traditionally like dependent path tree. But just like Han mentioned, right? So in his application, IE application, he will prove that Chris is wrong. But I want to say a little bit more about that. Is that so? There's no good way to measure that. So if the current graph is optimal to the function task, so to our experience, it's always good to have a different way to capture a different dependency. The transformer essentially is learn something very similar to the dynamic graph that we are talking about here. Only difference that we have this sparse graph, but the transformer you learn a fully clean graph. But this type of the approach only capture, I think, only capture certain language pattern that behind the word sequence. The dependency path tree is a kind of a domain-specific knowledge that essentially, I believe it will be a little bit different, or at least provide some additional information. But that's just my my explanation. I believe Han will give a more explanation on that when he talk about the IE applications. So Chao talk about some work showing that pre-training sequence model like BAT or the T5 can receive randomly initialized graph as input to achieve the decent performance as graph to text generation, such as MR to text. Any suggestion about how to use graph neural to enhance these generation models? So this is a great question. So recently we have seen a lot of the pre-training model. People have been pre-training for BERT, pre-training for the sequence, and even right now people are doing this pre-training for NLP, showing that it can achieve the decent performance. But I think this is very task specific. When we say decent performance, how decent? Is this close to the state of art, or is this still have some gap? In general, I believe that the power of the graph neuronals is that it's able to take into account the graph structure that is maybe come from, for example, a static graph that is constructed by domain knowledge, or either from a dynamic graph that is capture some semantic meaning between the different word token. So that means that it goes beyond the original text sequence information. So from the information entropy perspective, definitely if you have more information regarding your input, you should be able to learn a better result. I don't know if other people have some Yui or Han or Yuyao, do you have any other answer for that?
So you are going to talk about text generation, right? Natural language generation. So do you have some example that can help understand at this point?
I think my overall feeling about the comparison between GNNs and the transformers, that when we talk about the performance between them, we are not doing like very apple-to-apple comparison, because the power of transformers are like mostly achieved by pre-training it on a very large data set, like using various loss functions and various pre-training tasks. The people and it has shown a great result on NLP and CV applications, but people haven't really tried applied a similar idea to the GNNs. Like people haven't tried pre-trained large scale GNN models on a very large corpus and compare the performance with the pre-trained transformer models on downstream tasks. So I think that will be a very interesting direction to look into. And I think there are some recent studies showed that like maybe we can like if we like pre-train like convolutional neural network on a very large corpus, like we can also achieve very decent performance on some CV applications. So not quite clear whether transformer is the only option for like supervised pre-training. We can achieve very good results by pre-training GNNs on a very large corpus in the NLP field. Yeah.
Yeah, we will actually introduce this as one of the future directions that the people should consider. I also asked, what's the endpoint for termination of the dynamic graph? We have already discussed that. So we have some kind of criteria to determine when to stop the dynamic graph learning process. Maybe you can send the paper inside the channel so people can take a look later.
Sure, yeah, I will do that soon, yeah.
Could you explain about the strategy to reduce the graph size by removing some node? So, we are not really removing any nodes. In the dynamic graph construction, we are adjusting the graph edges by increase, for example, the sparsity of the graph, so that we can remove some graph edge that is not really useful for downstream tasks. One of the very simple way to think about that is that, for example, if we use a transformer to learn a flattened graph, right? Some of the graph edge could be a very small number. Okay, so that means that that could be some kind of like a similarity score that could be kind of noise. So that should be removed. Okay, this is just one simple example of motivation. So why we should learn a sparse graph instead of have a flattened graph. And we also have been showing in our experiments that so the sparse graph indeed will perform better than flattened graph. So we already sent a paper in the chat, so people can take a look at that paper. Consideration of the graph formation makes that our DL model need more or less data point to converge. I think I had that we need to build a model that learns smarter with less examples. Yes, this is a great point. And I believe that today pre-training model, people have been very fascinated in the pre-training model is one way to think about to train a big model, and then for every task, you just use a very specific less data point to fine tune that and then to solve the problem. But this is a very active area. How to learn from less data is a very active research area. Are there any few short unsupervised approach in graph for NLP? So far for the graph neural nets, we have been implement inside our library. It's just the graph neural nets that we introduced here. But indeed, for the graph neural nets, they also have an unsupervised approach, try to learn a graph node embedding. But be aware that so the unsupervised graph representation learning approach typically will perform worse than the semi-supervised method. So if your application have some label information, you still should consider the unsupervised or supervised method, unless that they don't have any label information regarding your input. In that case, so then we can consider this unsupervised approach. By the way, our library is intensely have a very good extendability, in the sense that so we have a very friendly user development interface. So we have been created a lot of example inside our example folder. So you can see that how we leverage the graph for NLP library, and then you can develop your own code based on our library to solve the problem. what's the difference between GN and transformer with corresponding constraint attention? So you want to answer Kevin's question?
Yeah, so the question is, what's the difference between GNNs and transformers with corresponding constrained attention? Yeah, so for vanilla like transformers, it actually considers it's actually doing like pairwise self-attention, which means like it considers the pairwise relationship among all the nodes. But there are also some like graph transformer models which kind of combines the features of transformers and the GNNs, which can do like masked self-attentions, where the mask is basically can be obtained by the graph adjacency matrix. And yes, and for GNNs, I think that for GNNs, like there's the GAT model, which also applies the very similar like mask-based attention mechanism. But for most of the GNNs which do not try to learn the implicit graph structure, I think they typically do not apply attention mechanisms.
So I still have a question. Are there any well-known graph approach on dialogue chatbot like dialogue GPT? So we are not really working on the dialogue domain. But just as we explained so far. So for the NLP domain, so if input is a sequence, so then we can consider to construct a graph, and then using graph analysis to work on that. We have if we treat like dialogue as a conversational reading comprehension problem, then essentially in each of the dialogue turn, you can create a graph, and then you can think about to treat it as a kind of a sequence of the dynamic evolving graph. I believe in the conversational reading comprehension, Yunyao will talk about this type of the application later. So hopefully that in later slides you will gain some inspiration about is any good way to formulate a graph-based method for the dialogue or chatbot. So finally, is graph for NLP friendly or for the multi-GPU processing? Yes, I think so. So our graph NLP library is built on the architecture for the existing library. So we are not built without consider any other library. So as long as, for example, we are built on top of the DGL, the Deep Graph Learning Library. So as long as the DGL can support the multi-GPU, even multi-node, then our library should be able to use on that scenario as well. But currently, we only support for the PyTorch version. The TensorFlow version is on development.
Yeah, I think thanks for all the questions. Maybe it's time to move to the application part.
Yeah. Okay, so now let's start our second part of our tutorial, deep learning for NLP applications. So Hen, now it's your floor.
Thank you. Can you see my slides okay?
Yes.
Awesome. Okay, so I will talk about the first application on information ingestion, just because it's naturally a graph ingestion problem. The input for any IE is basically a natural language sequence. It can be a sentence, can be a document, or can be a corpus. And then the output of IE is usually a graph, and we can call it in many different ways. You can call this as a knowledge graph, or maybe information graph, or information network. You can have a node that represents an entity, and then the edges are showing the relations involving entities, or maybe some events that involve multiple entities. So in this tutorial, I would like to talk about 5 different aspects of this problem and try to show why graph deep learning methods are very powerful to not just improve the quality and also improve the portability, which means we can transfer what we have from one language to the other, from one data modality to the other, and also help us extend the scope of the injection. So instead of just doing sequence to sequence on sentence level, we should be able to gather together the prior knowledge from a corpus level, large collection, and then do injection also on large collection rather than on sentence level. And then finally, it can help us promote some really nice new applications using IE results. Okay, so as I said, the typical information injection framework will look like this. We'll have a sentence as input, and for each token, we'll have some sort of embedding representation. For example, you can use bird embedding to represent every token. So for example, the token here, 19, will have a different meaning from 300. And then we'll do beam search to decode a graph from this input vector. So for example, when we look at the token 19, we'll try to first figure out whether this is a beginning of an entity. And if so, it will also look at the left and the right of the sentence to see whether this entity is involved in any event that's already labeled. Okay? So we can scan through the sentence from left to right and then try to generate multiple hypotheses. So basically, you can think of this as a sequence to graph problem. You encode a sequence and then decode a graph out of the encoded vectors. And recently, actually at this year's NAACL, we have tried to extend this framework from sequence to graph to graph to graph. The reason is because as you showed in the many different ways of constructing graph in NLP, we have some other types of graph which are constructed in a lower level from semantic parsing, from syntactic parsing. So maybe we should be able to use that on top of the sequence encoding, right? So why is that? Let's look at one example here. In many sentences, especially news or scientific literature, you often see the entity is far away from the trigger. So it's very difficult to find the corresponding arguments for events, for example. And in that case, if we can compress the wide content using semantic parsing, for example, here, this entity initially was very far away from the trigger, but after we do abstract meaning representation parsing, AMR parsing, we can see it's only about 2 hops away from the trigger. And then we can consider this as our candidate argument for the trigger. So that's about the encoding part. That means instead of just looking at the left and right content of the sentence, maybe we can look at the global content from the graph. And then we can use a neighborhood of each node to help us enrich representation of each node, each entity, each trigger. So that's the encoding part. And similarly for the decoding part, usually in the traditional framework, we look at the whole sequence. You just scan from left to right. But if we look into the graph, we can then look at every trigger and then only check the branches under that trigger. For example, if we already identify murder as a trigger, then when we are looking for arguments for murder, we don't have to look at this branch in this graph, because presumably everything else, the arguments should be connected to this trigger within the graph covered, subgraph covered by murder. So that can help us narrow down the scope of search and also improve efficiency. So putting these two things together, we'll usually encode the sentence using a semantic parser, and then take this graph together with the original sequence to encode each node and each edge, and then we'll decode a information graph from the AMR graph. So to be more specific, when we are looking into the encoding part, usually we should take some attention network that will consider the different weights of edges, because it will be pity if you ignore the different types of edges that already come from the semantic parser, right? So here we decide to use, for example, edge conditional GAT to encode each entity and event node so that the information from the neighbors can be incorporated effectively. And then during decoding, we again still use beam search. The only difference is the order of the nodes during decoding are determined by the hierarchy in this graph in a top to down manner instead of going from left to right from the original sequence. Okay, so just to show you quickly, before and after we use the graph encoding decoding, this middle column here shows the sequence to graph results. So for example, here Washington is missing as a argument for this airlifting movement transportation event. But using the AMR graph, we make sure that the distance between this entity and the trigger is much closer than the original service distance in the original sentence, so that we can identify this Washington as agent argument of this movement event. So that means we can use graph models to really improve the quality of information ingestion from any single language, right? And also from sentence level. So now I would like to talk about how we can extend that to other languages. So the idea is that if we have a lot of we have plenty of training data resources for English, can we transfer that to do information ingestion for other languages? And this is not a new problem. Many people have been working on entity ingestion, cross-lingual transfer, but much less work has been tried for structure transfer because we have much fewer resources, and also it involves the structure. So maybe we need to really look into the input graph so that we can look at the language universal encodings. So let's look at this example. The left side is English sentence, the right side is the Russian sentence, and they're not parallel. They're talking about different things, even though they involve the similar types of relations of events. So we look at the left one. If we run universal dependency parsing, we can then convert this sentence into some hierarchical tree, which will look like this. So if we look at the connection between these two entities, person and facility, we can see the edge is a passive noun and then object, right? And then similarly in the Russian sentence, even though they are talking about different things, but the connection between these two entities look identical compared to the English side. So that inspired us, maybe if we can convert all the sentences from all the languages into some sort of universal dependency parsing results, then we can use maybe one common GCN to encode all of them. So you may ask, how can we make sure that they are aligned into the same space, right? So for each node, we can use multilingual embedding to initialize the representation. So that means after we do the initialization using the original multilingual word embedding, we can then propagate the representation of the neighbors to each, from the neighbors to each node. So for example, if the previous layer, we have the initialization for each node, now in the current layer, we can then look at the hidden representation of each node and then aggregate all the neighbors to add that into the original embedding. So when we are initialize the node embedding, we can also leverage other kind of symbolic features. For example, you may have a multilingual speech tagging, you may have a multilingual entity ingestion. So you can also use the types from that kind of language universal output, put that into your initialization of the representation. And now after we have that common GCN-based encoding common semantic space, now the problem just simply becomes edge classification, because we already have the pairs of entity and entity or pairs of trigger and entity. We simply need to classify that into one of the predefined event type or event argument rows. So now we can train the model from English and then apply that to another language. So here, for example, you already have many annotation on the left side, and on the right side, we don't have any annotation, but we can train the model simply using English training data because everything is already represented using this language independent GCN. So applying this kind of model to so if we train it from English and test on Chinese, we can see that the performance can reach about 59%, which is very close to what we can get by training the model from Chinese training data, which includes about 3,000 event mentions, which is about 3,000 sentences. Okay, so that's very encouraging. That means, if you can somehow encode the different languages using one structure, one common structure, and then you can train model from English and apply to other low resource languages. And this inspired us, maybe we can also try similar idea to do cross-media transfer. The reason is because in images and videos, they have much less resources compared to natural language about event injection or relation injection, right? So the idea here is to train a model from natural language and then apply that model to identify information from images. So we propose a new task. The new task will take image and along with the natural language together as input, and we are going to decode the knowledge graph from both of them simultaneously. So for example, here from the text, we can find agent and artifact. From image, we can find the vehicles involved in this movement event. So the basic idea is very similar to what I have already described for multilingual setting. The only difference is that we need to convert each image into a graph, right? So there are many different ways you can do this. First of all, if we already have some object detection system for this domain, then we can do we can identify those objects, and then we can run some parser which is called situation recognition parsing, which is very similar to the semantic labeling in NLP. Basically, they take about 1,000 frames defined by FreeNet so that we can identify each bounding box as a trigger, for example, here throwing, or an entity, and also their coarse-grained semantic rows, right? So this should be good enough for us to represent the initial input graph. And in many cases, the object-based graph is not enough because general news domain covers so many different topics. So we also can try, for example, using attention-based graph, which means this part of the heat map is really aligned with some certain semantic rows. For example, this part is aligned with agent most strongly. So we'll merge these two types of graph and then using GCN again. And then we need to find some sort of weakly aligned data, right? So naturally, we can use image and caption pairs. So for each caption, we can then use the similar idea we presented before, encode AMR graph together with the BioSTM using the input sequence. And then we can map these two GCN results into this common semantic space. So for example, here you can see the this heat map usually will be aligned with some sort of protester words in the captions frequently. And similarly, bus will be aligned with some other vehicles frequently. And now using this common structured semantic space, we can then merge any training data we have from natural language and any training data we have for images, put them together using one encoder, and then we can train a model from this merged resource, then test on any new document. And the new document can include these different data modalities, can have image and can have surrounding body text. And these two paths don't have to be aligned, right? So I would like to show some quick examples to show why we need a structure, right? So first of all, why we need a multimedia common space. You can still, if you don't have that, you can still try to do single data modality injection. But if you look at the results, like on the left image, if we don't have the text information, most image systems will fail to identify this as a ploy. They will mistakenly identify this as a protest because of the lacking of analysis on the emotions. But if we look at the text side, it clearly says it's a very beautiful, very happy play. So we can combine that information to determine this as play instead of protest. On the right side, if we only look at the text side, search is not a frequent trigger for arrest, so we're likely to miss it. But if we look at the image, the visual features can indicate there's an arrest event going on. So by combining the multimodal embedding, we can then determine this as arrest event. So compared to cross-media flat representation that ignore the graph structure, we also can identify many more argument rows more accurately. So for example, in the flat representation, this man will be mistakenly identified as agent just because the similar visual features maybe appear frequently as an agent. And we also have the I need to stop my video for 1 second. Yeah, so it also shows that this person is likely to be agent just because of the, maybe his hat or the surrounding surface contact. But if we look at the whole structure, which means other types of entities have some certain semantic role labeling results already in the structure embedding space, we can identify this person as an entity who is being arrested. And the structure can also help us in the cases where the bounding box is very vague, or when we have a crowd of people, it's hard to determine which box is aligned to which entity. So for example, here we can identify this whole group as artifact, which is missing in the flat representation. Okay, so that means we can improve the portability. And now let's look at the fundamental problem of information ingestion. The reason we only limit to sentence level, mostly because everyone wants to use sequence to sequence or sequence to graph, right? Because it's usually very expensive to represent the whole corpus, right? But usually information or events repeat themselves, history repeats itself. So if we can somehow encode some knowledge from large scale corpus offline, we should be able to use that further to improve event ingestion or maybe even define some new problems. So for example, if we look at other events involved in a civil unrest, we'll naturally find some patterns. So we call this kind of patterns as a schema. So for example, here you can see there's a civil unrest. Under this, we'll have different event types. You have a coup, have international intervention, and then these different events will be connected through temporal or causal relations. And if we can encode this kind of schema from historical data, we should be able to use it to guide us for better decoding of our information graph. Okay, so what I mean by that kind of knowledge is that, for example, usually an attack event and a movement event are connected through different types of entities or different relations, which means if we already identify something as a artifact role of movement as a vehicle, then we can infer this vehicle should be an instrument of attack, regardless of the content it described in the input text, right? So that means we not only can use this as a global feature to infer more arguments, but we can also use this to predict what's going to happen next, right? Because a lot of the information just repeat, and we really don't need any evidence from text to do the prediction. So that inspired us to maybe we should really induce a schema automatically as a graph. So for example, if you look at all the paths between these two event types, maybe we can rank them based on some criteria. So the first criteria we should consider is salience. If this path appears very frequently, we should consider that as part of the schema. And the second criteria we should consider is discriminativeness, which means this path should be salient for this particular scenario, right? And that also means it should be coherent with other paths that appear in the same graph. So we use two criteria. The first one is simply to count the frequency of this path. And then the second one is look at every pair of paths to see how many documents they co-occur together. So to compute these two measures, we can simply consider each path as a sentence and then use something similar to the language model. So we call this as path language model to rank the different paths. And then after we induce a schema, we can then simply encode that as a global feature. For example, the troop that's involved in the transportation, the person involved in transportation usually is located in the destination place after they move to the destination, right? And if you look at the sentence itself, it's very difficult to identify this located in relation between the person and the location because they are far away from each other in the input sentence. But using the graph schema, we can infer there's a located in relation between these two entities. So using this, we are able to improve every IE component significantly, especially for relation injection. Okay, and then after that success, we are thinking maybe we can forget about extraction. Maybe we can just do this schema induction and use that to predict future events, or maybe predict any past events that are not reported in the document, right? So for example, if we look at this graph, after we know this person has learned how to make a bomb, then we can predict maybe they are going to purchase some materials to assemble the bomb. And after they assemble the bomb, maybe there will be attack event happening unless the bomb was removed. So this kind of schemas can be learned from historical data, and then we can use that for prediction. So how do we do the prediction? We can use the graph generation model that Yu and Linfei have already described. So we basically start from a small part of the graph. For example, we already know there's attack followed by die, and then we can predict next event should be arrest, just because this type of event happens very frequently in the historical data. And then we can predict what's the edge connecting these two events. And then we can predict the edge connecting two entities involved in these two events and their relations. And then finally, we can predict the temporal order, whether this event happened before or after the previous event. So, so you can think of this as an event generation model starting from a few nodes and then grow incrementally until it covers all the possible scenarios. So why this is powerful? Because if you compare the results with the prediction based on human written schema, human schema cannot cover all the possible scenarios, and the human schema cannot have a very reliable probability counting because it's not data driven, right? So for example, given these two, given this sequence or this graph of events that we already observed from the data, we can see that the human schema mistakenly predict there's going to be a sentence or child hearing event, just because usually you see this kind of events after attack. But the problem here is this person, this attacker is not arrested yet. So unlikely there will be a child hearing or sentence event that will happen next, right? So our graph schema can predict arrest first, and then there might be some broadcast event, maybe some die and injury event following that attack event. So the accuracy is much higher than human schema because of these two reasons. All right, so finally, I would like to talk just quickly about another new problem. So I just want to say this kind of graph representation is very powerful because if you look at this, instead of the sequence representation, you can have many new problems to tackle. So the example I would like to give is about misinformation detection. Usually people just look at the fake news document as a document and classify it as a fake document or not a fake document. And the features you use is just embedding or maybe some linguistic style, things like that. But if you look at the real scenario, when we look at the whole corpus about one complex event, for example, here I show a misinformation that says this woman soldier is patient 0. But the problem is she was never tested as positive for coronavirus, so she did not get virus. But the human is really good at connecting the dots, right? So they look at her activities that happened in October 2019. She went to Wuhan, and then she came back, and then she's also affiliated with the US army, so likely, there's something going on here. So that kind of connection make people believe that this kind of misinformation. So our task here is to be able to find not just like the whole document is fake, but which piece in the document is fake. And then we can fix it, and then maybe we can generate a new more authentic narrative. So because of interest of time, I'm not going to do any introduction with the audience, and I know many people are very shy, so I'm not going to do the quiz. I'm just going to show you some examples comparing the real and the fake document. So comparing these two, the right side is fake because all this red information is fake. The entity is not related to this organization. This event did not happen. And in many cases, the fake information exists in the captions just because it's easier to manipulate the caption. For example, from this image, it's hard to tell whether these soldiers are leaving the facility or they just arrived. So this arrived caption is fake. And this image is hard to detect this is in Berlin or Milan if you've never been to these two cities, or maybe if you're not familiar with the street scenes. So the manipulation happens in changing location. So that means in addition to the linguistic style and topic shifting, these kind of features have been used in previous work, maybe we should really look into the knowledge element level, look into a knowledge graph, and try to figure out which subgraph or which knowledge elements are wrong, and then we can fix them. So compared to previous work, we are now looking at the multi-model and looking at the knowledge element level detection. So the whole idea is that we are going to use the multimedia knowledge graph construction that I already described, and then looking into every triplet in this construct multimedia knowledge graph to see whether that's real or fake. So for example, here from the image side, you can see the police was not shooting at the crowd, but the caption says the police was shooting, and the body text says there was a woman who was permanently blinded, and this event was not shown in any other part of the document, right? So that means if we can construct the multimedia knowledge graph, then we can look at the consistency across the different triplets. And if one triplet does not get enough support from other data modalities, maybe it's a fake triplet. So that means here maybe the attack event did not happen. The blinded event also did not happen. So this also requires us to do some sort of cross-media event coreference and entity coreference going beyond the extraction, because we want to make sure that this police node from the text is the same as this bounding box that extracted from the image, right? And then we can do graph propagation within each data modality. We can try to check the consistency, and then we can check across different data modalities whether they are consistent or not. Okay, so that all looks beautiful, but now we are facing a bigger challenge, which is we don't have any training data. So the work I would like to talk about, which is very important, is how to generate training data automatically. So we would like to simulate how human will generate fake news. Basically, we are going to look at the authentic news document and then construct knowledge graph, and then manipulate the knowledge graph by replacing some knowledge elements or changing some edges to other types, and then use graph to text generation to generate a new training data. So this kind of manipulation has many different advantages because you are really looking into what kind of information is most misleading and what kind of information is already grounded. So maybe you should not change it, right? So this can move us to as close as possible to how human generate fake news, right? So we did two types of manipulation. The first one is to manipulate the information graph. So we'll simply construct multimedia knowledge graph and then replace some entities and then replace some edges or adding things. So for example, here we're going to replace maybe the bicycle as a truck. But then the problem is because bicycle is already presenting the image, this kind of generation result is very easy for human to detect, right? So we don't want that. So we make sure that our manipulation does not apply to anything that's already grounded in images. So we're going to replace, for example, Zambia as a Fiji, because Zambia, this country name is not grounded in the image. And these two countries have similar semantic embedding representations. Okay, so the other thing we tried is to use AMR graph to do this kind of manipulation, because AMR graph covers more relation types and it's not limited to any domain. And we can also see things like negation. So we apply this to manipulate the captions. So for example, here, initially it says attack, and then now we change that event into hiding. And maybe initially it says this event happened. Now we can change that to did not happen. Okay, so the first question is how effective this kind of generation method is, right? So we did a tooling test. We asked a human to look at the real and fake information to see, pairs of documents to see whether they can detect that as a real or fake. So for the other fake documents, the detection accuracy by human is only about 42%. So that means our generation is very powerful. It can even mislead human. So now we compared our results with the previous models. So Grover is a sequence-to-sequence generation model for fake news detection and generation. Dedan was a model that was published last year at Nlp by Boston University. So they tried to also use sequence-to-sequence, and they look into multimedia information, but they did not look into the graph structure. So compared to these two methods, we can see we achieve much better results on both data sets. The first data set is generated by Grover from New York Times. The second data set is from us. So we use a knowledge graph manipulation, and we apply that to a lot of Voice of America news documents. So you can see for both data sets, our system achieved much better performance. And also for the knowledge element level detection, our performance is better than random. But you can see that there's still very big room to improve for this new problem, even though like document level detection accuracy is very decent already. And here just showing one more example. This image shows another facility and the body text talking about twin towers, which are not grounded in image. So our system can detect it. And the sequence-to-sequence model failed. So I don't think I have time to show the demos, but we'll share slides. You can play with these. We have some demo to show the using the construct graph for event recommendation, or showing them on heat map so that we can do better resource allocation. And most of these systems, all of them actually are available as source code and Docker containers. So you can feel free to play with them. With that, I would like to hand over to you again. Thanks. I think we can take questions at the end of this application session.
Okay, so let me.
Oh, sorry. It's no. 白云阳, not 白云.
Okay.
So let me stop sharing. Sorry, forgot that. Oh, I just want to have a quick comment about the question in the chat. So a big disclaimer is that we're not going to share the generator. We are not going to share the generator at all. We are going to share the detector. That's a big disclaimer. We don't want to generate fake news. We want to use that for training. Okay.
Okay, so I'm having. Can you see my screen?
Yes, we can.
Okay, but I'm not seeing my. Just a second. Let me try again, because it's not sharing in the way I wanted. So. Just give me a second. Okay, let me see. So maybe you can start with the later part. I'm having some problem getting my slides.
Yeah, sure. So maybe I can talk about my part first. Then
Yeah,
you can,
yeah. Please go ahead.
Yeah. Okay. Let me share my screen. Can you see my screen?
Yes, we can.
Yes, we can.
Okay, yeah. Just wait a second. My laptop is slow now. Okay, let's get started. So in this part, I will talk about the application of GNNs in natural language generation and machine translation.
You didn't fully, you didn't enter into full screen.
Yes, because I think my laptop is a bit slow. I think it's okay now. Okay, yeah. Yeah, so let's talk about so one of the natural language generation application, which is natural question generation. So the task of natural question generation aims to generate natural language questions from a passage and an answer. And ideally, the generated question to the given passage and answer. And the generation task has many useful applications, such as providing training data for question answering systems. So this paper introduced an RL-based graph-to-sequence model for the question generation task. So it contains RL-based graph-to-sequence, gene-based graph-to-sequence generator, and a hybrid evaluator, which combines both the cross-entropy-based loss and RL-based loss. So we will focus on the generator part in this tutorial. So basically, the idea is to treat each word in the passage as a node in a graph and apply a graph neural network to better capture the structure of the passage. So let's talk about the graph construction part. So this paper explored two graph construction, and specifically they leverage the dependency graph for static graph construction, and the other strategy they use is the semantics aware dynamic passage graph construction. And specifically, they use the node embedding based similarity metric learning and the KN style specification to get a sparse graph from the fully connected graph. So all these technical details we have already covered in the methodology part, so I will not delve into those details. And then let's talk about the graph representation learning part. So this paper, for this paper, because the input graph is regarded as a homogeneous graph and it's a directed graph, so the authors leverage the bidirectional GNNs to encode the directed graph. So more specifically, they applied the bifuse version of the GGN model as the graph encoder. And here we can see that the authors compared the results of the static graph construction versus the dynamic graph construction, and it seems from the results that the static graph construction performs slightly better than the dynamic graph construction, but the performance gap is actually quite small. And the advantage of the dynamic graph construction is like it does not need any domain knowledge. And the results also showed that the bidirectional GNNs performs better than the directed GNNs. And also the GN-based graph-to-sequence model performs better than the sequence-to-sequence model. So now let's move to another application, which is question generation from KG. So the difference is that the input knowledge source of this application is the KG instead of a passage. And so we are given a KG subgraph and a target answer. The goal is to generate natural language questions which are relevant to the KG and the answers. So this paper actually applied a kind of similar idea to this QG from KG tasks, where they applied a GN-based graph encoder to encode the KG subgraph and apply a like LSTM-based sequential decoder to generate the natural language question. And in terms of the graph construction part, they leverage the knowledge graph construction way. So specifically, they first identify the top entity of the mentioned in the question, then they just extract the subgraph surrounding the top entity from the KG and use that as the one of the input. And the other input is the answer set. In terms of graph representation learning, because it's not a homogeneous graph, it's a KG subgraph which contains variance, node types, and edge types. So we cannot directly apply homogeneous GNs. So the authors first converted the non-homogeneous GN graphs to the homogeneous graphs. And because it's a directed graph, so they applied bidirectional GNs. Again, they also use the bifuse GN as the graph encoder. And they also applied another variant, graph encoder variant, which is the multi-relational GN. So in that variant, they directly introduce the edge embeddings, which captures the semantic meanings of the relations of the KG, and to encode it. And the multi-relational GN is able to encode the multi-relational graphs, as we already discussed. And the results show that the Lavie graph conversion plus homogeneous GN performs comparable with the multi-relational GN. And the relation study also shows bidirectional GNs performs better than the directional unidirectional GNs on this task. And now let's move to the summarization application. So the goal of this application is to take as input a document, a dialogue, a code, or multiple documents or dialogues, and tries to summarize the key ideas of the input into a few sentences. So this paper again leverages the GN-based encoder to encode the graph representation of the input code, and it tries to generate the summarization, which is corresponding to the input code. So, and for graph construction, they exploit both static graph construction and a dynamic construction. And they kind of combine the intrinsic graph structures and implicit graph structures, as we discussed in the methodology part. And as for graph representation learning, so since the input graph is not a homogeneous graph, it's actually a multi-relational graph. So they apply the multi-relational GN as the encoder to learn the representations of the code graph. And a hybrid GN was proposed to run message parsing on both the static graphs and the dynamic graphs. So the results shows that combining static and dynamic graphs performs better than single by only using a static graph or using dynamic graphs. So this actually shows the benefits of combining these two different ways of graph construction, and I believe this is also a very interesting research direction to explore more. So now let's move to the machine translation task. So goal of this task is to translate a source language text to a target language task. And so this paper proposed a GCN-based encoder to capture the syntactic information of the text. So they specifically they apply the multi-relational GNNs because the dependency graph is a multi-relational. They treat that the dependency graph as a multi-relational graph. And the results show that encoding syntactic information using GCN is helpful. Now let's look at this multimodal machine translation paper. So in this paper, so multimodal machine translation is basically so compared to the traditional machine translation, it takes as the image as the additional input. So because the image is agnostic to languages, so like different languages can describe the same image. So the image information hopefully can help the machine translation task. So that's the key idea of this multimodal machine translation task. And in this paper, they propose the application-driven static graph construction process, where they connected the visual nodes to the linguistic nodes by using some rules. But for the visual nodes or linguistic nodes only, they just fully connected the visual nodes and the linguistic nodes. So so because this is a heterogeneous GNN, so they also supply the heterogeneous GNN to encode the multimodal graph. Yeah, so that's my part. Maybe we can move to Yunyao's part. So let me stop sharing.
You unmute yourself. Cannot hear you.
Yeah. Okay. Can you see my screen?
Yes.
Okay, great. Yeah, so I will talk about the two NLP applications. The first one is semantic parsing. So let me first briefly talk about what is semantic parsing. So semantic parsing is the task of giving a sentence, parse the sentence into the corresponding meaning representation, which then can be executed and then obtain the needed response. So one popular task in semantic parsing is the task of text to SQL, also known as the natural language interface to databases. So in this task, the input to the semantic parser is a natural language question, and also often with the corresponding database schema or the entire underlying database. As you can see from this very simple example, right? We have two sentences. If you look at the sentence level, they look very similar, but because of the underlying database are different, the actual query look very different. So this really captures why we need to leverage graph neural network. We want to better capture different type of database schema. So the first early work on text to SQL using graph neural network is this paper published in 2019, where the schema structure is captured in graph neural network. To capture the database schema, it learns a representation for every database constant, which can be the table name as well as the column name. They are captured as a node, and the edges are basically connecting tables and a column, as well as the primary key and the foreign key relationship. So you can see from this simple graph, we basically have two kinds of node. One is in bold, those are tables, others are a column. And then we also have dust red edges that are foreign key edges, and then gray edges are table column edges. So every question refers to a different part of schema. So therefore, in the graph, you can see some part are highlighted, some part are not. So the highlighted part are the part of the database schema that's related to the current question. So once the graph is constructed, I gated the GNN used to learn the graph embedding. So in this work, self-attention is used to score a schema item based on its relation to previously decoded the schema items. And then score of the schema item increase if substantial attention is put on the schema item to which it bears high similarity. In addition, it also have a relevant score, which is to change the graph representation conditioned on the actual question, because the relevance of the schema item depends on the specific question. So basically, with combination of the self-attention and the relevant score, we can really capture constraint from the question as well as from the schema. So if we look at the actual results, right, obviously, if without the graph neural network, it's really not performing well, which means that encoding the schema structure is really important. In addition, you can see if we remove any component of the graph neural network, we are going to see significant drop in terms of accuracy. This also means that all component in the graph neural network is important. So one thing you may notice, right, when I talk about this particular work is that it only consider local information. It not really consider global information. So in a follow-up work from the authors, they actually propose something called a global GNN, where it shows that not only we want to make decision of the schema item based on the previously decoded one, but actually look at the global context of the query as well as the database. So is the input to the gating GCN is actually the same graph as we discussed just a couple minutes ago, except we add a new node called the V global. So this is basically the new node that capture all the other nodes. So it's connected to every single other node with a special edge type. And then the relevant score probability is computed per database constant based on the final graph representation. And so as you can see here, right, this part we try to take into account the global information that globally attend the input question as well as the entire database schema. In addition, there are also a re-ranking part. And the re-ranking part is really try to concentrate on the main pinpoint of zero-shot parsing. That is, we need to make sure that the set of database constants that appears in questions are all considered in the final query. So unlike the gating GCN, the re-ranking GCN take input only in the subgraph introduced by the selected database constant and the global node. So the global node representation is to describe and score the question conditioned on the subgraph. So we compute for every single question word, a representation of the database constant is aligned to. The goal is to allow the model to recognize whether there are any attended words that align with database constant, but are not selected by the current predicted query. So we want to really capture the obvious mistake that there's some constant mentioned in the question, but not appearing in the query. So the final results, as we can see here, that introducing the way to be able to globally reason about the structure of the output query to select the corresponding database constant is really effective. So if we remove it, we will see over 3 percentage point drop. Similarly, re-ranking queries based on the global match between the database and the question is also effective. So you can see in this particular work, right, graph neural network actually using 2 places and both places are quite important. Another recent work on leveraging neural network for graph neural network for semantic parsing is fact-checking over table. The work is called the logical fact checker. So this task is giving a table and giving a statement, classify whether the statement is refuted or confirmed. And then it also have a corresponding program that reflect this logic reflected in the statement. So this is the overall architecture of this particular work. first step is graph construction. And then based on the graph construction, construct contextual representation, which then used to attend the underlying BERT transformer. So I will just first describe the graph construction. So the graph construction is done in the following way. So we have a statement, we have a table, and a program. For each table, the nodes are the columns, cell, as well as the rows. And every cell is connected to the corresponding column node and a row node, and the cell node in the same row are also fully connected with each other. So that we construct the part related to the table itself. And then for each program, it's already in a tree, right? So we have functions and arguments. Each of those are represented as a node, and they're also hierarchically connected along the existing logical structure. In addition, arguments are also linked to the corresponding column names in the table. And then in the statement, each token is a node, and then they are connected to each other. In addition, they're also linked to the corresponding cell or column in the table, and also legitimate argument in the program. So you can see the graph really fully captures the local information and also the connections across different input. So this was used to construct a graph-based mask matrix, which then used in self-attention in BERT. So if we look at the final results, without graph mask, we see a pretty, not a very significant, but evidence drop, which means the graph mask is really quite important. So this is an interesting work, where some of you asked about how do we combine graph neural network with BERT. So this is one such an example where by capturing the graph and information, we can use to better improve performance of BERT by introducing self-attention. So in summary, as you can see from the work I just described, graph neural network is effective in semantic parsing by better capture the global constraint and related context, and it also helps with alignment between questions and the corresponding meaning representation. And all graphs are constructed in an application-driven way related to the ontology that we described earlier. So the next task I'm going to talk about is machine reading comprehension. So on a high level, the machine reading comprehension task is task of giving questions, giving underlying unstructured, sometimes semi-structured data source, extract an answer or select a correct answer from a given list. So one particular type of machine reading comprehension task I'm going to talk about in the context of this tutorial is called multi-hop reading comprehension. So in this particular task, the main difference is that the answers are not extracted through a single document or a single paragraph. It requires reasoning across different data sets. So in this task, we have questions which include the source entity, relation, and unknown answer entity, and then also a list of options of candidate entity. So the task is giving external resource that can be unstructured or semi-structured, for example, Wikipedia or Wikidata, select the corresponding answer entity. So here you can see some example from WikiHop. So the first one of the early papers that leveraged GNN for multi-hop reading comprehension is this work by Chao et al. At NAACL 2019. So in this particular work, it first constructs something called the entity graph. So the entity graph, basically, you can think of it, is extract all the entities from different documents, use those to construct nodes, and then it constructs the edges across the node in different ways. So one is based on document. If two nodes co-occur in the same document, then they are connected through a certain type of edge called the doc-based edge. And then it also have match-based edge that based on exact match. If two mentions are identical, they are also connected with use this edge. And then they also have coreference edge. Then for any other node that are not connected, it has a complement edge. So you may wonder, right, like why they're also merge and coref. So coref is the have more, better coverage, but it's less reliable, as you will see later on through the results. And the match provide a more reliable link between mention, but then because often the same entity can be mentioned in different way, right? So they're not as the coverage will not be as good as coref. So the graph representation of each node is learned by entity relation graph convolutional network, and basically gated version of relational GCN. So you can see here the actual formula used to compute all the things, and corresponding to what we have talked about before, this is not a homogeneous graph because it has different edges, right? And it's not converted into homogeneous graph, but it only have one kind of node type. Then we use a multi-relational GNN for this task. And finally, the candidates are scored based on the final node embedding and also the question representation that are used to predict a distribution over all the candidates. So you can see here in this formula, we have both the question representation and the final node embedding. So look at the final results through ablation test. So we can see removing the relational GCN resulting quite a bit drop, right? So it means that the graph neural network is really helpful. And then if we do not consider different type of relation, we will also see a drop. So it means that relations are really important. And then if we remove different type of relation, you can see the difference here. The most important type of relation are document-based. The others are kind of quite similar. And then finally, it tried to introduce some edges, like it had an alternative method to actually learn to introduce edges, and then the results are not so good. It means that learning to predict edges in a graph is still a very hard and open problem. So another thing I want to mention is on the performance side. So you can see the number of candidate answer or number of nodes increase. You can see performance drop, for both cases. The reason really because, when you have more candidate answer or more nodes, it just results in a larger and more complex graph. But you can see the drop is not very sharp. So it means that it's actually reasonably scalable approach, but definitely more work needs to be done here so that it can scale better. So another work, a follow-up work to this by another team kind of captures what we just discussed, that in the entity graph, it's only taking entity level information into consideration. It has different type of edges, but it only has one kind of node, right? So in the follow-up work in NAACL2021, introduced additional two kinds of node, candidate nodes as well as document nodes. So it first basically generate query-aware candidate document and mention vector representation with co-attention and self-attention. So the co-attention enables the model to consider interdependency between queries and document, query and candidate and mentions. And the self-attention pruning summarizes information presented in the co-attention output by calculating a score for every word in the sequence. So the actual graph you can see here is has different type of nodes. It also has many more type of edges. So on the high level, there are 7 type of edges. So between the edge between document and candidate, if they appear in the document, there is that. So if the entity extracted from the document, there is an edge. If an entity dimension of the candidate there are also edge. And then similar to what we just discussed in the entity graph, the co-occurrence and the corref as well as the exact mass, they all result in additional edges. And once all the contextual embeddings are initialized in the graph, I gated the GCN is used to train the node representation in the graph. So this is similar to what we just discussed. And then finally, the final node representation of candidate and the entity nodes corresponding to mentions of a candidate are used to calculate the classification scores. And through the ablation test, we can see the hybrid, the HDCE graph is effective. And then you can see the edge types are important, similar to what we just seen earlier. The entity node are more important. We, in this work, right, introduce the candidate node as well as the document node, but entity node are more important, which is not surprising. You know, the improvement over the past work is mostly due to introducing additional type of node and edges, but the entity node is really the most important part for reading comprehension, right? And we can also see similar decrease in runtime in performance as the number of the support document or candidate increase. So again, it's also because as in, you know, more number of document or candidate there, you know, there is a larger graph and more selection confusion and more complex in terms of the entire computation. And then another task in the also within machine reading comprehension is called textbook question answering. So here you can think about the input document are no longer individual document. I mean, the document are textbook. So textbook compared to typical document, when we think about it, like Wikipedia, it's much longer. It contains additional information like in graphics and so on. So this is what this work try to address, be able to really take care of the fact there is a longer document and then there are also multimodal information. Yeah, so the key challenges are what I just described, and you can see the difference here, right? The average length of context. So in this particular task, it's much larger than in a typical machine reading comprehension test, and the same with another thing is also, if you think about textbook, right? One textbook different from the other very significantly, which means that if you read, you know, if the machine learn from one textbook, it may be hard for the machine to be able to apply the learner model over that textbook to another one. So we're going to see how the authors address the problem of solving unseen problems. So this is the overall architecture where it's basically similar to what Han and also we talk about with multimodal setting, right? So basically the graphs are built based on different kind of input, like diagram parsing, and then also from the text using dependency parsing, build a textual context graph as well as a visual context graph, diagram graph, and so on. So the embedding phrase, the embedding step use the recurrent neural network as a sequence embedding module and the GCN as a graph embedding module. So with attention method, we can get a combined feature. So after concatenation, RNN and the fully connected module can predict the final distribution in the solving step. So if we connect to what we described earlier on the graph embedding learning, this can be viewed as the homogeneous. For each of the graph, it can be viewed as a homogeneous graph, and each of them is an undirected graph. So one step I was talking about earlier, right? The challenge of dealing with unseen question is this particular work apply self-training. So essentially, it will use the validation data set without the label. And then use the validation data set is assume typical, the traditional TF, IDF returns reasonable results, and use that to create self-training steps so that the model can learn to read and understand a textbook and problems in advance from the validation data set. So now we're going to see how effective each of the steps are. So you can see the self-training is very effective. Even just the self-training over the training data is already useful. And of course, the most useful thing is really the context graph. So you can see the largest drop when we remove the context graph. Finally, I'm going to talk about one use case where it talk about using dynamic graph neural network. So in this task, it's a task of conversational machine comprehension. So given one piece of text, it will have multiple questions in sequence, and one question can build on top of the answer of the other. So unlike the traditional machine reading comprehension, we really need to look at the topic shift as part of the conversation progress to make it harder to model a conversation. And also many of the questions refer to the previous question. So if you think about the machine comprehension task we just talked about, right? The model only need to handle one question at a time. But in conversational machine comprehension, you need to take the entire history into consideration. So in order to do this, it uses a framework that contains three layers: encoding layer, reasoning layer, prediction layer. So for encoding layer, it uses a by-LSTM to encode a question and another by-LSTM to encode context for each conversation turn. So the main contribution of this work is actually in the reasoning layer, which has the context graph learning component that dynamically construct a question and the conversation history aware context graph at each turn to model semantic relation among context word. And then it also has this context graph reasoning component use a novel RGN and relational GNN module to model a sequence of context graph in a conversation. So which we will explain more in the next slides. And then finally, the prediction layer that predict answer location by matching question and the context embedding. So because the context embedding already takes the question as well as the previous history into account, right? So the prediction layer basically going to capture both information as well. So the most important part is really the context graph, right? Which basically dynamically construct a question and a conversational history aware context graph at each turn. So this is what it does at the high level. So when performing reasoning over context is basically viewed as graph of words that capture rich semantics relation among words, and then apply a recurrent graph neural network to process a sequence of context graph. So this RGN module combines advantage of RNN, which are good at the sequential learning, and GNN, which are good at relational reasoning. So this is at a high level, how we do this graph embedding learning. And you can see by visualizing the change of hidden representation of context word between subsequential turn by computing the cosine similarity of hidden representation of the same context words at a subsequent turn, and then highlight the words that have small cosine similarity score. You can see as the conversation focus shift, right? The part of the text that are important for the question also changes. It also give us some level of explainability of this work. So finally, as we just discussed, for machine reading comprehension, this graph neural network enables multi-hop reasoning, and it also enables us to really encode heterogeneous information from different source or different granularity. So I need to end. Okay.
Okay, thank you, Yao. Let me share my screen. Okay, so far we have done the application part. So since we are kind of run out of time, so we will continue with demonstration part, and we will have a QA session after this tutorial session. So so now is our hands-on demonstration. I don't know if you guys have already clicked the link for our Graph4NLP library or not, and also download the demo code. So let me first introduce our Graph4NLP library. So this is the first library that we have been developed for the easy use of the graph neural net for NLP domain. And this is the overall architecture for our NLP Graph4NLP library. So we from the hardware side, we support the CPU, we support the GPU. For cluster, is we haven't support yet. So for the backend framework, so far all the code is developed based on PyTorch, and we have active development for the TensorFlow. Beyond the this deep learning framework, we also rely on the core NLP. That is a Stanford library. This is a very important library that help us to, for example, to get the aesthetic graph construction. So another layer is a runtime library. So some people have discussion in the chat about the deep graph learning library and PyTorch geometry. So one thing we want to highlight that, so we do have many comparison between different library. So the reason we prefer DGO over the PyTorch geometry, there's no way to say that the DGO is better than PyTorch geometry. They all have their own advantages and disadvantages. So the reason we choose a DGO, because we feel that so DGO is very actively maintained and have a lot of the new development, especially that it's a support for the large scale computation by supporting multi-GPU, multi-node computation. So that's the only reason that we choose DGO as our runtime library. We also, based on the Hugging Face, that we use Hugging Face to compute to get the pre-trained BERT embedding, so that we can run that GN on the top of that. Okay, so the core part of our Graph4NLP, the Graph4NLP consists of 4 layers. The first layer is the data layer, that we have divided our graph data to effectively to carry out all the computation. And second layer have 5 different modules. So it's our module layer: graph construction, graph neural nets, prediction module, loss module, and evaluation module. We also have our model layer, in a sense that so we have been integrated, like for example, graph sequence, graph tree model inside our library, so that people can easily using that. You will have a demonstration in the code section later. And graph is a very active area. There's no very well-known architecture for that. So we are still working on this, and hopefully we can add that into our library later. The last layer is application layer. So we have been, this is just a demonstration, some of the applications that we support here. And also we provide many example code inside our library, so that you can either using this example code to perform this task, or if you have your own task, you are also welcome to using our Graph library as your backend library to do the active development. So because we already have a lot of integration for like graph construction, all this stuff, so it should be very easy to develop a very similar code, follow the example code to do your own applications. So let's dive into our Graph4NLP library. So as we mentioned before, so for Graph4NLP library, we have modules, and we have a graph construction, GN, prediction, loss evaluation, and we have all sorts of the static graph construction, dynamic regression, and you can see that so our tutorial is also have a very similar format as we are showing in our Graph4NLP library. And in the application level, we have supported many different applications, and hopefully this is provide enough example code for people to start. And so here is kind of a data flow for our graph NLP. So conceptually, so you have this raw text data, and you will code a graph library code for the graph conjunction, and then you can get the graph structure data that inside the library, and then with that will go to the user model, and then we'll get the repetition learning algorithm to generate the node embedding, and then later we can do the prediction. And in the result, in the evaluation, you have this loss function that's also provided in our library. And this is kind of a computing flow for the graph NLP. So for example, if you have a text sequence, so you can go through our static graph construction part, but this is optional because you can also choose a dynamic graph construction later. And then we will formulate graph data. In the graph data have two important jobs to perform. One is to do a topology construction. Second part is embedding construction. Okay, so once we finish that, so if you have already choose the static graph construction, you just need to skip the dynamic graph construction, or you can, if you haven't choose that, you can choose the dynamic graph construction here. And then we will feed the graph data to the graph representation learning part, and we get the node embedding, graph level embedding, and we can perform a different kind of applications. It's a node name graph prediction or sequence tree graph decoder for do the encoder decoder models. Of course, that's for some NLP applications, naturally they already have graph. For example, AMR to graph. Then you can just feed the AMR graph to our graph data, and then you can call our different modules to perform the task. So here's some example performance for our built-in NLP tasks. So we have been using different tasks, different dataset, different graph neural nets models, and different graph construction, and use a different evaluation metric, and to show you that the performance is close to the number that is reported in the paper. Okay, that's all for the introduction of brief introduction about the graph NLP library. Now I leave the floor to the Yu.
Great. Now it's a live demo time, so let me first share my screen. Can you see my screen? Okay.
Yes, we can.
Yes. So yeah, great. So yeah, let's talk about our first demo, which is to build a text classification application by leveraging GN techniques. So because it's a live demo, so you are encouraged to go to this demo page and to play with the demo when I go through this live demo session. So I also copied this link to the chat. So now let's maybe go to the demo page. You can see the demo page, right? Okay. So yeah, so this is our tutorial demo. So in order to run our demo, you will need to do some setup in environment setup. So the most important thing to install our graph for NLP library. So you can create a virtual environment. If you would like to do that, then the most important step is to install the graph NLP library. So you can clone the GitHub repo and just install the package from source code. So you will need to specify whether you want to have installed CPU version or a GPU version. And so this step, set up a Stanford CoNLP. So this is actually optional. The Stanford CoNLP tool is used for static graph construction, because it provides some tools like dependency parsing, constitution parsing, IE parsing, and so on. But for this demo purpose, you don't need to set up Stanford CoNLP because we already provided the pre-processed data, so you don't need to do that. After you install, after the finishing the environment setup, then you can start a Jupyter Notebook service and run the demo. So if once you start a Jupyter Notebook server, you will go. There will be that will open a web browser that will go to this web page, so you can click the demo files. So let's first look at the text classification demo. So in this demo, we will use the graph for NLP library to build a GN-based text classification module. This model we are going to build consists of 3 major components, which includes the graph construction module, the graph embedding module and the prediction module. So we will use the built-in module APIs to run the model and evaluate it on the data set. So if you already finished this environment setup, you should be able to directly run this demo by click Save Run All. So now let's move back to the slides. So I would like to introduce some of the major components in this notebook, where we call our library APIs. So here's some, let me just go to the presenter, just wait a second. So here's the overall model architecture. So it contains the graph topology, construction part, the GN encoder part, and the classifier part. Let's go to each of them. So for the graph construction, so you can directly call our graph construction APIs. So there are various building options for both static and dynamic graphs constructions. For static graph construction, we provide like a dependency graph, constitution graph, IE graph, and so on. And for dynamic graph construction, we provide variance metrics like the node embedding based structure-aware similarity metrics, and we also provide a variance graph specification operations to do that. And by the way, you can also customize your own like graph construction module very easily by leveraging our APIs. And for the graph representation learning part, again, like we provide a variance, GN variance, and you can specify whether you want to turn on the bidirectional GN option by specifying the specific parameter for this GN API call. And again, this can be customized. And the classifier, as for the classifier component, here we directly call the a building API provided by this library. This is basically so this component basically takes as input like node embeddings and it will apply a graph pooling. So you can specify like a variance graph, the specific graph pooling operations you would like to apply. For example, the max pooling, average pooling. So the graph pooling operation will return you a single vector to represent the whole graph. Then you can apply a like multilinear perception to do graph level prediction, which is what we are doing in this text classification application. So by the way, for this application, we regard each node in the text as each word in the text as a node. Then we build a dependency-based graph to represent the text. And again, like there are various building options in terms of the prediction. So we provide both classification based prediction APIs and the generation-based prediction APIs. And here you can also call a dataset API. So there are various building options here to handle like a comprehensive set of data sets, like for example, the text-to-text, the double text-to-text, or text-to-label, etc. So you can very easily build your customized data set class based on our low-level APIs. Okay, so now let's go to the second demo, semantic parsing application. So I also maybe go to the specific demo page. So in this semantic parsing demo, we will use the Nlp library to build a GN-based semantic parsing model. So the model consists of the graph construction module, graph embedding module, and the prediction module. So you can see that this is actually a very like a generic pipeline for many NLP applications if you want to apply GNNs. And here the difference is that we will use the built-in graph to sequence model APIs to build the model. So in the previous the demo, we call more like low-level APIs, but for this specific application, we will directly call the built-in graph to sequence model APIs.
and evaluate it on the jobs data set. So let's go to the slides page. Okay, so yeah, so because we will just call the high level graph to sequence model API. So it's pretty simple. We just directly call this graph to sequence API provided by the library, and we can specify various parameters regarding the which type of gene you want to use, which type of graph construction you want to use, like either it's a static graph construction or dynamic graph construction. And you can also choose what kinds of sequential decoder you want to use, like whether you want to apply attention mechanism, copy mechanism, or coverage mechanism. So there are many building options there. So you can also call the dataset API, which is quite similar. So I want to talk a little bit more about this dataset API. So here you can specify, because the static graph construction is conducted during pre-processing. So if you want to apply static graph construction, you might want to specify the specific static graph construction you want to use, like either it's dependency based or IE based. And also this library supports combine the intrinsic graph with the implicit graph. So if you want to go this way, then you can also specify which kind of static graph you want to use, and then you can also still turn on the dynamic graph construction component, which will try to combine both the intrinsic graph structure and the learned implicit graph structure for better model performance. Yeah, so that's my part. Let's move to the future directions and the conclusions.
Okay, thank you, Yu. Let me share my screen again. Okay, now we are into the last part of this tutorial, DLG4NLP future direction and conclusion. So as we can see here, so the both graph neural nets and natural language processing have been a very hot topic in recent years. So there have been this is not only happening in machine learning conference. This is also happening in NLP conference. And there are many open directions that still have been underexplored. So the first one I want to highlight is graph construction for the NLP. So as we see it from so many different applications, the dynamic graph construction approach, although it's very promising, but still currently is very largely underexplored. For example, how to effectively combine the advantage of the static graph and the dynamic graph is a very valid question. And also, nowadays the dynamic graph construction currently only support for undirected graph. How about that? How about if we want to develop some multi-relational homogeneous graph like static graph? Can we do that for the dynamic graph as well? So this is also a very open question. And also, for graph construction itself, it's not cheap. So if we use like self-attention based method, it's essentially a quadratic complexity in terms of number of graph node. So can we make the graph construction part itself also scalable? So this is all very interesting research direction. So for the many people consider about large graph, that's indeed true, that how can we scaling the graph neurons for the large graph? Most of the multi-relational or homogeneous graph neurons, they have this scalability issue, especially, for example, when we're doing some NLP tasks like catching the node graph. Typically, the size of the catch graph will be more than 1 million. So how can we deal with that? This is also a very open research direction. So many people have been already have a lot of discussion in this group that talk about graph neurons and transformer. The question is that, so I don't think graph neurons and transformer are two counterparts. Okay, Instead, I think they have their own advantages. How can we effectively combine the advantages of graph neural and transformer is a very interesting direction. So currently, some people have been trying to develop, for example, called graph transformer, trying to leverage the both advantage from both worlds. But is this a better way to explore that? So this is also some questions that we need to answer. And we have been talking about a lot about the pre-training language model for NLP today. Okay, but for graph neurals, there's very, very few work to do pre-training graph neurals for, especially for NLP. So I'm working in the JD.com. We have encountered a lot of search problem to do the searching and the recommendation. So there are many information retrieval problems and the problems that essentially is regarding NLP, right? The querying, the candidate, the title, all this stuff is a text sequence. So can we leverage the power of that gene to pre-training that so that we can use it as a very effective feature for the search system? So this is a very open question. And regarding the graph learning in NLP, so have been introduced some sort of early attempt how to develop a graph learning model to solve the problem. But this is very, very natural because for some of the applications like information extraction, you try to generate an information graph from text. And for some others, for example, the AMR graph that people have been extensively used as an input, but actually the AMR parse itself is also an active research area. So then we are talking about how to translate the input text into an AMR graph. That is also a graph translation problem if we treat the input size as a graph. And finally, we also can consider like joint text and catchy reasoning in NLP, so that we are not only using GN for the multi-hop reasoning, but try to explore the knowledge from both catchy side and also the text side, and then to do a more effective reasoning. In the catchy construction part, so we have been thinking about how to incorporate the source and the context information together to do this logic graph construction and verification. It's also a very interesting, at least in the IE domain. So to conclude this tutorial, so as you can see, the deep learning on graph for NLP is a fast growing area today. And the graph is a very, very natural way to encode the complex information. That's because that is bridge a gap that try to bring in empirical domain knowledge and the power of the deep learning. For any kind of NLP task, there are two key important questions we should ask. First of all, how to convert text sequence into a best graph? Is directional, multi-dimensional, heterogeneous? And second, how to determine the proper graph representation learning technique so that we can make a full use of the graph that we have been constructed. And we have been also introduced our graph NLP library that we have been developed for about like 1 year. And we are very glad that today we are finally released that. And our purpose is try to let people to make an easy use of the graph neurals for NLP. And here we release the code, we have a demo, we have the GitHub literature list. We also have a survey paper on the way. Probably we will release it next week. And we hope for that you will find this useful. And that's all for today's talk. Thank you very much. Now it's a Q&A time. Hello?
Yeah, we can hear you.
So shall we go back to some of the questions, because I feel that some people question maybe you haven't really answered yet.
Yeah, so maybe we can go backwards, go from the last question.
That's right, that's right. Oh, at the same time, so if you are feel free to unmute yourself and ask questions directly.
So, Linfei, maybe you can take a look at the questions.
Sure. Yeah, I was just wondering, so which is the starting point?
Max question, I think before the questions above that, we kind of give partial answers.
So one of the questions is, how is the density of the graph affect the accuracy? I'm going backwards. Just
Oh, that's question in the first part, right? I think you have me try to answer that question before. So
Yes.
general speaking, maybe you can repeat what you said before.
Yes. So because so for like dynamic, for example, for dynamic graph construction, because our ultimate goal is to have the best downstream performance instead of have some very like high quality graph or explainable graph, because we actually do not have the ground truth graph structure for some specific applications. So like which kind of like what kind of like density is the best is really it really depends on the I think specific downstream task. So we can use some, so for graph specification, like we can use some hyperparameter, like the k for kn style or the epsilon for epsilon neighborhood specifications to kind of to choose the hyperparameters in order to get the best performance on some downstream task.
I think some people are asking a lot about the medical domain. So, Yunyang or Henry, you want to summarize so your opinion?
So has been a lot of work converting sentences into semantic parsers. So that's related to graph. And a lot of people have been using external knowledge base. So you do anti-linking and then combine knowledge graph embedding with text embedding. But my impression is a lot of those methods are kind of using existing resources. So the modeling side, the work is not as deep as what we have been doing on general news domain. So there's a lot of potential great directions to explore. And also in biomedical domain, there are some domain-specific issues. So for example, if you look at some chemical entities, they have their own molecular structure. So some people have been working on using graph embedding to represent those kind of graph structures. Maybe Yunyao, you can add more about medical domain. Yeah.
Sure. I think as you mentioned, right, in medical domain compared to general domain, actually many other domains is that medical domain actually have lots of domain knowledge already in structured form. So they have a lot of different kind of ontology, right? So for example, if we think about the reading comprehension task we described, right? When they build an entity graph in the medical domain, I think, for instance, the kind of edges for correct and also for exact match will need to be much more complex, that actually taking the external knowledge ontology into account to build matches of the dimension. And of course, just identify mention itself is also a much harder problem in the medical domain simply because of the complexity. Yeah, I think the work we described today, right, do not really have any constraint on domain, but I think for specific domain, it will be very interesting to see what kind of additional information can be leveraged when we build the graph. Because I think the power of the graph neural network is really, it provides a very elegant way, right, to combine information from different sources. I agree, it's can be a very interesting application, also potential motivational use case to build even more sophisticated graph neural network approach.
Yeah, so I have been mainly working on literature, like the technical report for biomedical domain instead of clinical notes. But I think one problem that Yunyao mentioned is relevant for both genres. So there are many concepts or entities that are not being explained in the context because the writers of these notes or technical reports, they assume the readers are also experts. So if you only look at the sentence level contrast embedding, you won't be able to really capture the meaning of those entities. So many people, including ourselves, we have been trying to look into what we can integrate from the external knowledge base. So for example, we can use the additional definition sentence of entity. We can use the properties, and also looking at the hierarchical structure in the external ontology. All that kind of information, they are very useful. So one thing I think we need to do some fundamental change is the representation side on the text representation. Most of the work like ScienceBird and BioBird, they are just different variants of the general bird, right? But something special needs to be done there, because those documents, they are usually multi-model, and how can we integrate the knowledge graph information as input rather than just to do simple linear combination. Yeah, so I would like to encourage everyone to think about contributing to the science domain rather than news or other, other things we are comfortable at doing. Yeah.
Yeah,
So,
it seems like go back to this future direction. So it's very exciting to see that how can we tupulate the graph neurons and transformer and the pre-trained GN, also NLP. All this stuff can be further explored to see that if it's be interesting to see how can we combine the existing domain knowledge of class, the very large corpus training like language model, and combine all this knowledge together to to do a more effective learning to get both text and context information.
yeah, I think Jason has one more question about the library. Do you want to take a look? Jason, thank you so much for all these great questions and comments. I really enjoy discussion with you.
So maybe I should read it out. Does the library working for the edge attribute graph also should the attribute in the edge be treated as an edge embedding? You want to answer this question?
Yeah, so I didn't see the question, but I think the question is about like if there's edge attributes in the graph, where like
your volume is very low.
Right?
I don't know why.
I think the answer.
Your volume is quite low. Your volume.
Can you hear me? Volume. How about now?
I think I can hear you. I'm going to turn off my camera just in case the problem is on my side.
Okay, then maybe I can also turn off my camera. So, yeah, so if there are some like rich edge attributes in the graph, then we can also encode the edge attributes to like edge embeddings. Then we can use multi-relational genomes to encode the to capture the edge attributes when learning the node representations. And we can also actually learn the edge representations by using the multi-relational genomes.
Yeah, so more directly, so that library work for the edge attribute graph now? The answer is yes or no. So the yes, the no is that so currently we haven't been implemented, for example, embedding parsing neural network and GCN or GN algorithm into our library. So we cannot directly use that. But why I say yes is that you can convert edge as a node. And if we're doing that as using a Nlp graph, then we can support a library can support working for the edge attribute graph. Okay. And second question, should the attribute in the edge be treated as an edge embedding? It depends. So there are many different ways to do that. So one way, just as we mentioned, if we convert edge as a node, then the corresponding edge attribute will be treated as a node attribute. And then you can just generate a node embedding for that. But you can also keep the edge attribute there and then to learn an edge embedding. But which way is better? It depends. So from our experience, we have seen that so although many algorithms, for example, the graph neurons like MPN, claim that it can compute the edge embedding very effectively. But from our previous, some of the experiments, for example, when I'm doing this logic graph to text, we found that so if we keep the edge and doing the edge embedding, this is the result is not as good as if we translate that age as a node. So hopefully it's answer some of your questions, Jason. Thank you for all the great questions.
So there is a question about when and where will those recordings be posted. So maybe Nlp, you can repost the link where we're gonna post the recording.
For the recording right now, I think it's handled by NAACL, and we need to get the link from them later.
Yeah,
but
I think I want to post the GitHub link.
Yes,
right?
so this is GitHub, our GitHub link, and we will put every resources in our GitHub link later. You can check our GitHub for the update. Thank you, everyone.
Yeah, you can also follow us on Twitter. We're gonna share it on Twitter too.
That's right.
We'll post slides maybe today, tomorrow.
Yeah, slides we can share today, I think. Yeah.
Yeah. We will convert the slide as a PDF and then we upload it to the report. Yeah.
Just to say a little bit about the future plans. Nlp is actually leading efforts to write a book about this topic. So.
Oh, that's right. Yes. Yeah, we haven't mentioned about that. Yeah, thank you for bringing up again. Yeah. So we are writing a book on the topic deep learning on graph that will be published by a Cambridge press. And Hen and Yu right now we are actively working on this project, and hopefully the book will be the digital version will be ready in the early next year, and the hard copy will be ready like before summer, hopefully.
Yeah, thank you, everyone. I actually have a quick question for everyone here. Just curious, people are very shy at speaking up. Is because it's the recording, or because I'm looking at the options for ACL because I'm chairing a demo session. I'm just wondering.
Maybe you can stop the recording now and then.
Okay, sure.
No, I'm
stop recording.
How to, so that I can learn how to organize this kind of event better.